All right. Hello, everyone. Hello, 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 hello. I hope you're good. and yeah, welcome back to another stream. Here we are once again. Uh, working on our memory allocator as usual. I should take this shirt that I was going to put in the washing machine. Um, and yeah, how is everyone doing? How's everyone doing? I hope you are okay. I slept well last night and woke up, and now we're going to continue. Hopefully, today is the last day of the project, or well, we always say that, right? But there's almost never a last day. There's always something to improve and something else to write. But we'll see. We'll determine that today, and hopefully, the stream is gonna be very long, just like the one from yesterday. Just because we want to work on it enough to the point that we say, okay, I feel decent, and I feel like good with whatever we have up until this point. Of course, our memory allocator is not going to be super professional, but it is a good memory allocator, right? Something that we are satisfied with. And let me turn on the blinds. Welcome to the morning. Say hi to the morning, everybody. So let me see. Is everything good here? I think so. And this is the way we go back to the usual setup. So that's all. Here I am. It's 7:15 a.m. as usual. And so, yeah, me. Do-do-do-do-do-do-do-do. And yeah, we're gonna start today. Let's start today. We're gonna do our stuff. And there are a couple of things that we have overdue, right? Like, or things that we said we were going to focus on. Um, I think one of the main ones is related to some changes that I did yesterday night. Very small changes, but like I was looking at the code base and then I noticed that there were some mistakes. There was like two mistakes. Very subtle, but they were bugs in realloc. I think it was realloc or malloc. I don't remember. But we'll take a look at those and what each of them introduced. And yeah, so let me switch to the coding scene first, and then yeah. Okay, so let's see. How do we switch? Over here. Yo, welcome, welcome, welcome. It is the coding scene. I know. Very relaxing, very pretty. The music in the morning, more than awesome. Welcome once again. This feels almost like, I don't know, I like this music because it feels like you're just walking into a restaurant. Like, I don't know, it has a feeling to it. So we'll see how it goes. Yeah, so let me settle down. Is there anything else we need to do other than drinking water to stay hydrated? I don't think so. Okay, so let's take a look at some of the changes that I introduced, which were two fixes for two blocks. Let's perfect. Okay, so we had this first bug, right? And the comment describes it, right? It's a fix on realloc. It's a bug on copying the user data to a new reallocated block when merging with the previous block. So what do I mean by that? I'm going to grab. Actually, no, I think I can just show what happened. So the old block's footer would be copied into the new block's footer. Yeah, it was something over. Where is realloc? Oh, this is realloc. It was something that here, I think. No, it wasn't here. Where was it? Huh? Wait, I'm sure it was around here. Yeah, there you go, over here. So there was a bug, right? And the bug consisted on when we were copying the user's information, right? What we would do is we would say, okay, grab the information from the previous block, or like from the old block. This is the new block, and then we would move all the information from the to the new block from the old block in this much information, which is the size of the old block. And the problem would be that remember that we need to also copy the footer because setting the size of the block overwrites whatever information the footer has, which is why we did this mem copy, right? And so for that reason, we had to go here to pblock uptr, blah, blah, blah. So what we had previously, if I remember correctly, was something like this. bk footer of the pblock. So we were saying like, oh, right, bring the footer of the old block into the footer of the new block. The problem with this is that since we merged the two, the footer of the sort of new block is exactly the same as the footer of the old block. And so we wouldn't be moving the information anywhere. And so the information of the user would be lost, at least the last 4 bytes of whatever the user had stored in that block. And so the fix was to put that information not in the footer of the new block, but like right after the information that we just copied. So we go to pblock upointer plus the previous size to go to, the first byte after all of the data we copied. And then we go back by footer many bytes and then we copy whatever was in the old footer. And so that is the first bug, and that's what this comment describes, right? And then the second bug is the one that you can see. It's the single edit that I made. And it's that previously we had this, where we coalesce blocks and everything. And notice something. So this is the case where we have to merge with the left block, right? And so what ends up happening is we reallocate, we merge with the left block, which was free. We copy, we remove it, we make sure that the footer is there. We merge the two blocks, but notice that p block is still free. We haven't changed anything about that. Then we copy the information to p block. Then we partition p block, and then we return a p block. But at no point in time did we change it from free to allocated, right? So we needed to add this line that sets p block to be allocated. That's it. So we had that mistake. Yeah. So now, great. Those were the two mistakes, and I think I want to comment this one. Let me make sure that I'm in the right branch. Yeah, look, and then git commit -m. It's not a feat, it's a fix. It's a fix related to realloc. And this fix is going to be fix when merging with left, block wouldn't be set to allocated. Then a little bit of a more detailed explanation is when merging with the left block and copying all over to it, like doing a reallocation. There should be a comma here. They're in a reallocation, comma. Copying all the information over to it during a reallocation. Let's see. The new block was not being set to allocated. It remained free despite having user data. Perfect. And then I think we can just push this. Awesome. All right, perfect. So that is like a little bug in Realloc, and we can verify this by running the tests. Just want to do a single test run with you guys. So what we can do is now we can run our memory allocator, at least the tests file here. So want to focus on, say, test realloc2. It's an interesting test. So notice that what happens. So let's do a run of this. Hi, BestCreeper21. Welcome to the chat. Welcome to the stream in general. I was explaining some bugs that we needed to solve. Penguin Operator, welcome. I don't know if you guys were here when I was showing the bugs that we had. Basically, yesterday night I was looking at the code, and I noticed two bugs, and so I just fixed them fast. One of them had to do with the fact that previously this line, instead of being this, was this, right? And so what would end up happening is we would move the user's information, and remember that, like, by the way our memory allocator is designed, whenever we coalesce two blocks, the information of this block's footer gets lost. So that's why we first store the footer of that block, and then we coalesce because we know it's potentially lost. And so what would happen is that after we do all of this, we wanted to, put that information back. Right? Put the information, the user info and the footer, back into the block's footer. The problem is that we would, this, although it seems correct, right, put it back into the block's footer. Remember that P block is now coalesced with this block. So now it's like a bigger block. And in fact, the footer of P block, which now is the merge of these two, is the same as this footer of the old block, right? Since block is now the end of that block. I feel it makes it a little confusing. But this footer is the same as this footer, right? They live in the same location of memory. So when we're copying this, we're doing nothing, right? And maybe not we are doing nothing, but we're copying in the wrong place. We don't want to copy it in the footer of this thing. We want to copy it like next to what the user just wrote or what we just moved from the user. So instead of copying at the footer of the block, which may be like very far away from the user data, we need to copy it right after the user data. So we go to the pointer of user data, then we skip all the things we moved, and then we go back by whatever the footer size is and copy what we actually had stored. So that was a problem, that data was getting corrupted. And the second problem is this line over here. This line never existed, right? This line didn't exist before. And what would end up happening is, if this is a case where you need to merge with your left, so this is realloc, right? If we need to reallocate a block and the left is free, we merge with the left. And when we merge with the left, oh, I like Vortrox. Hello, welcome to the chat. Yeah, here I'm explaining a little bug we had in our code from yesterday for a memory allocator. But yeah, guys, so this is the case where you need to merge with your left. So when you merge with your left, right, you remove from the right black tree, you merge with it, and then you copy the data. But notice that to merge with your left, the left has to be free, right? So at this point in time, the left is free. At this point in time, the left is free. It's free, right? P block is free. Here we copy the information, but P block is still free. We do all of this, but P block is still free, right? It's always, always free. And so we give it back to the user, and the block is still marked as free. So we need to make sure that that block, after we merge it, is marked as allocated. So set that it's free to false. And that was the other problem we had. So those were the two bugs that I fixed yesterday night. What language is this? This is C. This is C. You can tell here by the extension of the files. C17, I think, is the version I'm using. But yeah, C17. I actually should name the stream "Coding the Memory Allocator from Scratch" in C. Thank you for that. Yeah, because that was the previous title. Anyways, um, yeah, coding Bara. Hello, welcome to the show again. And yeah, all right. So I think that for today, I just want to do a little test run of Realloc, which I have already done, but you know, just want to have a little peace of mind. We're just gonna run this small test, this test Realloc 2, and see how it behaves in the memory inspector, which is gonna be fairly simple because I think I verified this yesterday night and it worked. Just to make sure nothing has changed, I wanna do it a little fast. So let's see. If we do 0x 1534567100559 B60. Yo, no way. That's a lot of code. Yeah, yeah. It like, well, I wouldn't say a lot of code, right? Like there's like many projects that are extremely huge. But we have 404 lines, which is very funny. We have all of these lines for our red black tree, almost around the same as the memory allocator, 395. And then we have some little tests and some header files here and there. It is a relatively small project compared to other things, but yeah, it is a lot of code depending on you know on how you want to look at it. But yeah, so here we initialize memory, and notice that a bunch of these tests are going to take place, and they're going to modify the memory. So don't worry, right? Okay, we enter test realloc 2. And remember, nothing has happened up until this point. The data that's here, completely bogus, right? Just how it would happen in real life. You don't know what you're going to get on the memory you just allocated. Well, you do know that the pages are going to be zeroed because the OS zeroes them and etc. But like, they're not. Anyways, okay. So what are we going to do? We're going to go here, right? We're going to say this is going to be, a block that we want to allocate is 40. And so we allocate a block, and then its size is 29, which 29 in hex is 41. But remember, the two least significant bits we ignore because they store some other metadata. So this is 40. This one's also 40. Notice that it's 28. And then the next one should spawn, I think, here. The 75 should be replaced by a 28 or a 29. Perfect. And so now we copy the information, right? We write down, this is a, here you can see it. This is a 40 byte long message, AA, right? Then we do this guy. So we code, this is a 40 byte long message, BB. Then we do that last guy, which we see over here. This is a 40 byte message, 40 byte long message, CC. Perfect, everything's there. Now we free block 1. So remember, block 1 is this guy. If we free block 1, the root of our tree should point to block 24, which is 18 in hex. Yes. Now we reallocate P2. So notice that P2, which would be this guy, the 2A, when it reallocates, we only have 3 blocks available, P1, P2, P3. It cannot reallocate to anywhere other than P1 and then reuse the space. So we need to merge P1 and P2 and then copy P2's information to the beginning of P1, right? That's what we need to do. And so if we do this, right, if we do realloc, we should be seeing that happen. So let's enter that call. Perfect. So we compute the size. That's totally fine. It's the usual. Let me, there you go. So the size is 72. We get the previous block, which remember, our current block is P2. So the previous block should point to the first block, which is 24. And so P block should be 24. And the next block should be something like 96. Well, yeah, like 96, something like that. Yeah, 120, 120. That's fine. We're not going to shrink. We're going to instead expand. We try and see if we can expand to our right. We cannot. We try and see if we can expand to our left. And the answer should be yes. Emacs Power User, welcome to the chat. Yeah, we're running a little, program to see if the realloc works. Then we take a look at the previous size of our block. So our block is previously 40. We remove P1 from the red black tree. We copy the footer's information because we're going to need it later. And notice that when we run coalesce blocks, the information of this block, of this one, right? Notice that it ends in BB and then 3 exclamation marks. It's going to get overridden. Exactly, right? Now it's an X and 2 nulls. So that's why we need to copy the footer so that we can save whatever was there. Then we set this block to be free. Perfect. We copy the user's info. So now, instead of 40 long message AA, this should be changed by BB. We continue. We move everything. Notice that it's BB, but it's missing the exclamation marks because it copied exactly what was here. And so now we need to bring back the exclamation marks, not to the footer of the block, which lives here, but to right after we copy, the space right after where we copy the information, right? So now we have it back, right? Now, the leftover block, it's going to be a product of saying, well, is this block too big? Which it kind of is, if I remember correctly, because currently the size of this block is P block 88, right? And we need to accommodate for 65, right? So it's still pretty big. I think we are able to partition it. So leftover block should be something other than 0. Oh, actually, we're not able to partition it. Okay, yeah. It was kind of in the fence whether or not to partition, but determine no. So we skip this and then we give this to the user. And then notice that the information is indeed reallocated, right? Information is there. We assert that the pointer is exactly the same because we shouldn't have, the same as P1, which is indeed true. And now we free P3. So when we free P3, we want to reallocate P2 to some sort to like a bigger space. And so now P3 leaves to the right of this reallocated P2, which means that we're going to try to merge with our right. So we take a look at everything, we calculate everything. We're not going to shrink the block, we're instead going to expand. And this is the case where we expand to the right, and indeed we do, right? We remove it from the tree, we coalesce the 2 blocks together, we try and see if it's too big, which in this case I would argue no, not really. So if we take a look at DK size of block, you see that it's 136, right? And we need to accommodate for 110. Actually, maybe. I think we would be able to partition, but like just by the exact amount. Because the requisite to partition is the difference between the block I'm giving you and the information you're storing is at least 20 bytes, then it's worthy of partitioning. So 110 minus 136, right? But remember that the rounding to a multiple of 8 may change how things work. So let's see. Leftover block. Yes, okay, so it got partitioned. Notice that it's now size 112 instead of the 136 it was before. And so now that little partition, we set it to be free, and then we insert it into the red black tree because that's the data structure that stores our free blocks. And then we simply return, right? And this is exactly what we give to the user. So now P2 should have everything. So no information should have been moved because we were merging with our right, so there was no need to copy. And then when we realloc, right, we obtain a pointer that should be the same as P2 underscore because we didn't move once again. And And then here we copy this huge message just to see that the block can indeed allocate that much. I see a bunch of messages in the chat. I just want to finish this thought. Not sure what they say, but I'll take a look at them. Okay. Just let me verify that this is correct. It says this is a 40 byte long message. Never mind, it's actually 110, or I think. Happy face, and then and then we finish in a 7 A's. 1, 2, 3, 4, 5, 6, 7. Yes. And then the null terminator, of course. Perfect. And then we have the free block that remained, right, from that partition. And we simply return. Good. So realloc logic in this case is fine. The last thing we need to check is what happens when we shrink a block, right? So it would be bool test realloc shrink. Okay, let me now read the chat and see what you guys are saying. Hi, Emacs Power User. I do study CS, but I don't have a real idea how to write a memory allocator. I like the no AI and plain C approach. Thank you. Yeah, I'm also in college too. So good to know that you're studying CS. Yeah. I mean, before starting this project, I also had no idea about memory allocators, but you just sort of go on the internet and say, what is a memory allocator? What is it supposed to do? Try to not look at any implementations or any code. Just be like, okay, I have an idea now, and then just go for it. Yeah. La Boo Boo Dubai. Oh my god, bro. La Boo Boo Dubai Chocolate. Yoo-hoo, it's a La Boo Boo. Yeah, anyway. Yeah. Can I ask why you don't use AI? I feel this has been a recurring theme through some of the streams. I'm trying to be I'll be a little concise because usually I go on a tangent. It is mainly for the sake of learning, right? It's the reason why we're writing the memory allocator. Didn't know about memory allocators as I mentioned to Emacs Power User, and I feel like a good way to learn is learn by doing. If I were to use AI, I think all of the learning process would be sort of hijacked, or it wouldn't be as effective, right? So my purpose is to learn to really understand, and thus part of that decision is not using AI. So yeah. Destiny Waits says same reason why artists on Twitch aren't using AI probably. Yeah, similar. Those are like yeah, they're not equivalent. It's kind of around the same in a sense. Well, not really the same, but yeah. Sometimes raw dogging blank canvas and code from scratch is fun. Has its own thrill though. Yeah, exactly. There is something that AI takes away from coding that I feel I want to rescue to myself. Make me a memory allocator, then it appears on the screen. What an exciting stream. Yeah, I mean, I'm not sure if it would be. Well, I guess AI would be able to create a memory allocator, right? Because there's a lot of memory allocators online. So yeah, I mean, yeah, it's an interesting position. But here we want to learn and have a little bit like appreciation for coding from the roots, or like from the beginning, and really enjoy what makes coding actually fun, I feel. Then segmentation fault cordon. Yeah. So okay. So let's see how can we test shrink. I think it's gonna be fairly simple, right? We say char star and then p1. Of course, we're gonna return true if everything goes well. Char star p1, and then when we do with p1 is we malloc. Remember our implementation of malloc is written as nalloc with an n. We nalloc, say 40 bytes. I think 40 pretty good number. And then what we do, we write some information. Let's copy into P1 some sort of string. Hello everybody. Everybody. This is 40 bytes long. Let's see if it is indeed 40 bytes long. Oh, yeah, exactly. 39 characters with the null terminator, that's 40. Okay. And then once we have this information, maybe I want to, create another block right beside this one. It's also 40 bytes long. And for which we have some information too. So this is P2's information. Thank you. Or like, the end is near. I don't know. We just need to write something that is 39 characters. And this is 41. This is P2's thoughts. I think that's 39. That's 38, so then we add an exclamation mark, and that's 39. Perfect. And so what this will do, it will create one block here, one block here. And what I want to do now is free this block, so free P2, and then, sorry, shrink P1 so that the free space over here is left there, and then free P2 and check that these two actually merge, right? So what we're going to do is, okay, char star P1 underscore is going to be equal to what happens if I realloc P1 to some other block that just has a shorter size, right? A shorter size of 20, right? Or 24 because it's a multiple of 8 and it's a little more beautiful. Once that happens, there's going to be like a tiny little bit of free thing left, right? Thing that if we take a look at this, right? I think I can just make it, 60. 60, it's maybe a better, actually 64. Yeah, 64 is like a little bit bigger so that we can actually see the partition. Prokopton, welcome to chat. Your space for the actual code is too narrow, brother. Only 17 lines. Yeah, that's because we have the memory inspector open because we're trying to test something. Usually the code and everything looks more like this, right? Just a little bit more while we're developing. But yeah, currently it's a little narrow just because we want to take a look at how memory is behaving. Okay, and so we have this char star P1, right? And then we reallocate it. And then we want to free P2. To see if the two of them merge. And then make sure that, all of this is possible by allocating some sort of new block. Oh, it's not mmAlloc, it's nalloc. Some sort of new block that is, so there's 64, 64, 128. So probably 128 bytes long, right? Then writing some sort of message. And actually, nope, it's 64 instead. There you go. So these are 61 characters. 62 and 63. There you go. So then we add this to the end of the message to make it 64 bytes. There you go. And now we copy to P3. We're also going to copy sort of 128 bytes. That's a lot of information. Not sure how we are going to fill that up with a single string and allocation. I think those are 128 characters. 127 characters, sorry. 119. Okay. The single string and allocation. Bye-bye. Is that 127? 130. So 29, 29, 28, 27. Bye. There you go. And that should be 127. Great. So now we copy that and then we return true. So let's take a look at how everything runs. Um, Prokopton, I see. Cool. At least today I will have learned something. Why AMD is called AMD. Though failed my initial task. Why is AMD called AMD? That's a good question. Wait. Why actually, where does the name AMD come from? Huh. Um, in the meantime, let me start executing this. So let's make, and then let's run this. Let's recall realloc shrink. So let's run this, and let's just, sanity check that everything is working correctly. Advanced micro devices. Ooh, I see. That's a pretty fitting name. We don't want to take a look at that. We want to take a look at realloc shrink. No, brother, no. No. Stop. Okay, yeah. There you go. So now we want to add a memory view for the heap that we have, which is 1, 2, 3, 4, 5, 6, 7, 1, 0, 0, 6, 3, 1, D60. 24 megabytes. So let's get into this function, right? And then remember, everything that's currently in memory, it's bogus, right? This just makes no sense because it's from the previous tests. So we're starting from scratch. And actually, never mind. I forgot to call memory init. Well, memory manager init, right? Let's reset. Let's make again. And let's run. Okay, so I have the heap, we have test realloc shrink, and we're gonna step into it. So the memory, once again, we need to go to the memory view because now the heap is different. 1, 2, 3, 4, 5, 6, 7, 1, 0, 0, 5, 7, 5, 5, 7, 5, what? D0, 0. Perfect. Oh, Emacs Power User, thank you for following and same for La Boubou Dubai Chocolade. La Boubou Dubai Chocolade. This is such a weird name. Emacs Power User Mantroop also followed. So thank you guys. So let's take a look at this test, right? POV, my text editor think my log is Chinese because it's like a half of it. Brother, what are you doing? So remember, everything here is bogus. Don't trust it. Okay. We initialize memory. The heap says at 0. We allocate the first block. So this 71, you should see converted to 64, right? Whatever 64 is in hex, which should be something like, 40, right? Yeah, like, what am I talking about? You should see this via 40. It's very easy what it, yeah, a 40, 41, remember, we don't care about the 2 least significant bytes, so that's also correct. We write the information, and indeed, hello everybody, this is 40 bytes long. Nope, it's 64 instead, right? And we see 2 dots. Perfect. We do the same for P2, so now we should see, I think it's gonna be this guy, changed to a 40. Yes. And then we're going to store all of the information there. So then it says, this is P2 starts, and this, the end is near. Nope, it's 64 instead, right? So now we realloc P1, and we have to be, we have to pay close attention to what's going to happen now. So remember, P1 starts here and ends here. So all of this is P1. Basically from this A all the way to here, right? So all of that is P1. We want to realloc P1. So what we should see is, let's step into it. We shrink P1. There is a tiny bit of block left. And then when we free P2, that tiny block is going to merge. So let's see. We calculate the size, which the size is, 24. Then we align it, and it's still 24. Then we calculate who we're talking about, the blocks and everything. The previous block should be null, yeah, should be like a bogus number. And then the next block should be pointing at P2, which should be something like 72, 96, something around that range. Yeah, 96. Okay. Then the space needed is going to be calculated, which is fine. And notice that we do need to shrink, right? Notice that the size, where is it? 24. It's definitely smaller than 64, which is the current size of our block. So we need to shrink. So we should enter this if. Perfect. And then we should consider whether or not we should partition. The answer is yes, because the difference between 24 and 64 is 30, which is greater or equal to either 16 or 20. I don't remember what the threshold was. So we do that, yeah. And so now the block has been reduced to size 24, which means that leftover block is now a block of a different size. Like 6, yeah, perfect. 32. So leftover block now needs to say, well, is the thing to my right free? The answer is no. So we skip this. And then, ooh, very tricky. Notice this. We have a bug. So if we say BK is free of leftover block, it says this thing is free, right? Wait, how? I think that's just a coincidence. So what I was going to say is, despite leftover block being a block that's going to be free, we never set it to free. It just so happened that like the memory that was previously there made it to be free, but it's not supposed to, right? Or like it could be the case that it is not, just because of like how memory is laid out. So at some point in time here, we should have done, marked this block as free, but we never did so. So that is something important and we need to do it. Yeah, so notice that we do it all the time, right? BK set is free and then insert. Here, we didn't do it, right? So yeah, we definitely need that. So BK set is free. Then we set it to be which block? Well, the leftover block needs to be set to yes, it's free. Right? Perfect. So let me now compile again. And let me actually add this as a fix with comment -m. Fix inside of realloc when partitioning block inside shrink path, right? Inside of shrink path. Well, I guess mark leftover block from partitioning on shrink as free. There you go. We reset, we push, we reset again, and then we recompile. Perfect. Okay, let's run it again. Let's run it again. We can skip some of the parts we've been looking at because like, we know those work. So over here, we enter this function, right? We know this works, we know this works, this works, this works, this works, and we go back to realloc. So now let's enter the memory view for the new heap. 1, 2, 3, 4, 5, 6, 7, 1, 0, 0, 6, 4, and then 9 CE0. Perfect. Okay. So we now do the realloc of P1, which is where we were. And at some point in time, we need to detect that this needs to be a shrink. Then we enter here. Yes. Here's a leftover block, remember? Leftover block is now size 32. We continue here, and then we skip this. We set the block to be free, which is something we forgot to do last time, and we insert it again. Then we return the pointer to the user, and the pointer should be pointing at the exact same block. So now here, P1 is exactly the same. Just notice that notice that the information is not hello everybody, this, da 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 da. It just gets immediately cut so that we can include the new free block, which is, 21. there is nonetheless an issue. So these 3 bytes should not be set to 0 nor 18, because this was information that the user was storing. So notice that we have size 24 now, right? And size 24 would imply if we have 16, 17, 18, 19, 20, 21, 22, 23, and 24. So these bytes were previously containing information. Now they're no longer. So we're corrupting the user's information. And that is an issue. That is an issue. We shouldn't be doing that. So when we shrink, we also need to keep track of, it's sort of the same situation here, right? Where we need to keep track of what the footer is before we do any changes, because the footer will probably get overridden by this new operation, right? So when we expand, right? No, sorry, when we shrink and we partition if it's worth it, then we need to store that block's like information, or at least okay, so part of the block's information, it's going to be overridden by the footer of a renewed block. So we need to store whatever was here before we modify the footer. We don't care about what happens to the thing on the right because that's free. So, no longer has information we care about, but we do care about this footer. So before, and this is a bit of an issue because when we do partition if worth it, we kind of don't keep track of these things. And we don't really know where the footer is going to be when we perform a partition if worth it. And so it ends up being a little bit of an issue. Yeah, this is a big issue. Because when we partition the block, right? When we partition the block and we set the size, not of the right block, but of our block, the size modifies both the header and the footer, and that's what's overriding whatever's on the footer. And so, yeah, so now we have an issue. Now we have a problem. We could make some sort of conditional, although I'm not sure how wise that would be. A conditional on saying, well, if the block you are partitioning is allocated, then don't override the footer. If it's free, do it. How profitable that is, like how wise it is, I think this is enough. So if the block that you have is free, then feel free to do this, right? So if it's allocated, well, I guess this is going to be the else instead. And this is going to be the if. So if blah, 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 blah. If it's allocated, we don't want to override the footer, right? The thing is, the way we do that, it's like user info in new footer. I don't know how to call this. But it's simply going to be equal to what? So the new footer will be positioned, and this is where we have to start doing the pointer arithmetic to know where we're gonna end up landing. it's going to start at the beginning of the block, right? Then it's going to skip the header. So we skip the header, we skip the size of an allocated block header. Then we skip the amount of, the size that this thing is supposed to have, which now is size needed, right? And then we go back by however many bytes a block footer needs. And that's the position in the heap where the footer is going to be. So, right, let's create just that variable and then let's do memcopy. So we copy into the variable of user info in new footer, right? Whatever is at char star, so the lowest byte of the heap plus all of this offset. And we copy as many bytes as a footer contains. I see best creeper. Oh, an example of how it looks in your eyes. Pretty good. Size of block footer, right? So if this happens, then sure, we copy everything there. And once that takes place, we set the size. And once we've set the size, we now make it so that whatever is gonna be stored in the footer is still there. So now we can do mem copy back into the new footer. And this time we can do it to the new footer because we just shrank. Copy into the footer whatever is in user info. User info in the new footer. And how many bytes are there? Well, it's just an entire footer. Okay, that should be it. So if your block is not free, then we perform the copy. So if it's not free, the block. There you go. Perfect. Too few arguments to function call. Argument block was not specified. Brother, I'm passing you this. Okay, this may just be Microsoft products being slow once again. There you go. Okay. Perfect. Perfect. So now let's run this again. let's compile it again. And compile it once more just to be sure that we're compiling correctly. And there you go. And now let's run it. So if we run this, we get to the heap, then we get to test realloc shrink. We initialize, we allocate all the things that we know are there. So let me first set the memory view. Should be 0x 1 2 3 4 5 6 7 1 0 0 then 6 4 9 3 0 0. Perfect. So here we grab this pointer, we allocate it. Perfect. We write information, we allocate, we write information. We know all of that is correct because we just saw it happen right before our eyes. We enter realloc, and here we should detect that we have to shrink, as we did before. So we should enter this if. Perfect. When we perform the leftover partition of worth it, this should just, partition the block to be something else, to be something smaller. Then we continue. Then we insert it, and yes. So notice that this is, 19, which should be 25. Yeah. So it's 24 bytes long. Remember, we don't care about the least two significant bits. So now we continue. And then here, when we want to realloc P1, remember, what does P1 store? It stores, hello everybody, this is 40 bytes long. Nope, it's 64 instead. So it's all of this, right? Hello everybody. Ooh. We still overrode the information. Why? When does that happen? Why? What? Wait, that is supposed to be changed. Okay, let's see what's going on. Continue. Oh, sorry, no, I didn't want to step over. Okay, we continue. No. Then we enter this function. Then P1 is allocated. We write P1. And okay, let me enter that memory. So address 0x12345671005A 5A9D00. So notice that here we have the information that we need. Hello everybody, this is 40 bytes long. Nope, it's 64 instead. And then no terminator. Okay? When we allocate P2, that information should still be there. And when we write P2, the information should still be there. So these 40 bytes are there. When we enter realloc, let's see what happens. So I guess what the first thing we should look at is we're going to shrink the block to be of size 24, right? And if that's going to happen, it means that we expect the first 24 characters to stay. So that would be these guys. Let's see. These guys. Hello, everybody. This is. If this is not present after we realloc, then we have a problem. So remember, we end at this is. So everything after that is allowed to be corrupted. Continue, 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 continue. Okay, we partition if worth it. And notice that that thing overrides the this is, right? So it becomes a problem. It's a serious problem. Oh, wait, Toerk Tumlade. Thank you very much. Welcome to the stream. Yo, we're getting rated. Yay. Yeah. Welcome to the 5 people joining. We're currently debugging our implementation of realloc. There seems to be something weird going on. Something strange. So yeah, I'm not sure. So currently, if we enter partition if worth it, right? The problem ends up being, so I want to inspect what is going on exactly in that function, because it's very relevant on why it would be overriding. So it's clear that it's overriding because it's set in the header, right? Sorry, the footer. But I thought that we just corrected that. So let me enter realloc and let me, refresh the memory view to whatever the heap is now. Which is 0x12345671005 FDB00. Hello. Okay. 0x12345671005 FDD00. Perfect. Okay, we're gonna realloc. Enter the blog. Notice that the this is still there, right? So then we continue, have the space needed, and then we enter this function, partition worth it. So we're gonna calculate how much space we're going to partition this by. We calculate the size needed. We grab the total left space, which is 32 indeed, right? Well, is it 32 though? Yeah, 24 plus 8, yes. After that, we perform the calculation and say, is it worth it? And the reason is yes. And then when we enter partition block, we should see the following. So we should see, these are just calculations. So none of them should affect memory. And indeed they don't, right? Now, the right block, right? Whoever this guy right block is, it's the block that's gonna remain free after we partition the block. So notice that this is address, here. This is gonna be like byte 32. This is gonna be byte 48. And right block is 56. So it's gonna be like over here. So this guy, this 20, is after the this is, right? Because notice that the S lives somewhere else. Right? The S, it's living up until like the byte right before, right? 3, 4, 5, 6, 7, 8. Yeah. 1, 1, 2, 3, 4, 5, 6, 7, 8. So it should start modifying from here. This 73, which corresponds to the S, should be totally fine. Let's see, the right block. Yeah. So 73 should stay put. Nothing should change. Yes. Then we set the pref3, which changes the 20 to something and the is3 to something else. Pretty good. So there's something we need to ask ourselves. Is the block that we're currently taking a look at free? The answer should be no. But it's yes. And that is a problem. Because our current block is P1, right? So P1 is the block that we're partitioning so that we can shrink. And for some reason, it is free. Still when it contains user information. And it means that the problem comes from upstream, because here we don't set that to be free. In partitioned with it, we don't do it either. So it has to be something else. Maybe Nalloc gave us a block and it just forgot to set it to free. Let's see. Okay, let me add the memory view first after we step. Okay, so it should be 0x12345671005 half 9d00. Brother, what happened? 0x12345671005 f9d00. Perfect. Okay, so we initialize memory, we do a bunch of crazy stuff. We enter this function, we go here. So take a look at P1, right? Right when we're about to return from P1, sorry, from Nalloc, we need to see whether or not that block is marked as free. Right? So you go here, we have to expand the heap. Yes, we expand it. We set its size, blah, 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 blah. I just need to get to the return statement. Here. So last block, which is what we're giving back, should not be free. Which I think is the case. Because I just saw that we set it. So false, right? It is indeed not free. So at what point in time does P1 become randomly free? Let's see. We get P2, right? Nalloc 64. Oh, I think I know where it happens. Yeah. Okay, I see where it happens. So there is a problem. There is a bit of a big problem. That big problem is the same that haunted us last time. So this is once again very subtle. We have to be extremely careful. So let me open Excalidraw here to explain what's going on. Notice that when we perform this partition of a block, right, we separate the two blocks, right? We set this right block to be some sort of, independent block. And then after that happens and everything takes place. Actually, no, wait. There's something wrong. Okay, no, we do have an actual bug. There's something weird going on. It's not what I thought it would be. Yeah, so at this point in time, if we enter realloc, right, we compute which block we're talking about. And we should be talking about block 24, which is P1, right? So let me open the memory viewer again, because I don't think what I'm saying is what applies. Maybe it is, but it seems to me that it is not. And it's still false, right? That block is not free yet. The problem comes when we enter partition of worth it here. Notice that it's still false. So then we enter. And the problem is going to be when we enter partition block and we create the new block, this thing is going to magically transition to true. If what I'm saying is correct, but I don't see. Okay, I would need to clarify why it happens. So my guess is like we create the block on the right, we sort of partition. And so now my original block's next is no longer the actual next, it's going to be the new block I just created. And this new block has no information set. And so it like completely doesn't know what's going on. But that shouldn't happen, right? That shouldn't happen because the block size of block 24 is 64, right? And we perform all these calculations and stuff. And when we set the size of this right block, things shouldn't change. This should remain false. This should remain 64. Yes. When we set the previous free of block, we set it to be BK is free, which is false. So it should still be false. But when we set the is free of right block, things go south, and for some reason, unknown reason, this gets flipped to a true, right? So why would that ever happen? Right block is currently living on space 56, which should be 3264 over here, right? And so when we set it to be free, it will look at the next block in the chain, which should be this block over here. So this 40 should be changed to a 42 when I press continue. It changes to a 42, right? Which is sure, correct. But okay, yeah. So it's something similar. Notice, okay, we have a conundrum. We have to be extremely careful when we do partitions because what's going on is this. So let's go to the Excali draw to take a look at what's going on. What's happening is, give me a second. What's happening is, oh my god, please let me erase the lines. Okay, we've been making very crazy drawings over the past few streams and it's been damaging our drawing of blocks. Let me erase this, and let me erase this too, and this, and this. Perfect, and then let me erase this guy. So what's going on is this. When, think of this thing, think of these two, this is P1, this is, think of this as P1. This entire guy, P1. And this one is P2. What's happening is when we partition P1, right, we say, okay, right? And I'm going to put this side by side with the code so that we can take a look at it. What happens is this, right? We make all the calculations needed to know where we have to split the block. And then we say, okay, the right block, which would be, whatever's going to be the leftover, we set its size. So by setting its size, we sort of mark that this thing is a block. P1 still thinks that it is of this size. But we're sort of starting to change the metadata so that by the end of this, we have two separate blocks. So we're setting the size, and by setting the size of this block over here, this block thinks it is already a block. P1 still thinks it occupies the entire thing. This is completely fine because, at some point in time, the state has to become invalid while we partition. This is fine. So that is the set size here. Then we set the previous free. Oh yeah, sorry, canvas override. Yeah, you're right. Sorry. There you go. Gonna move it here. then we set the previous free of the right block to be block is free. So now, remember, the way we tell whether or not a block is free is by looking at the next block, and the next block tells us if the previous one is free. And this we did to save some space, right? So if I want to know if P1 is free, I take a look at P2, and P2 in its header, in its size, it's going to store the information of whether or not its previous block, in this case P1, is free, right? So just have in mind, if I want to know if P1 is free, I take a look at the next block, in this case P2, and then ask it, is P1 free? So we're going to set the previous free of the right block to whatever P1 is. So we want to make it so that this new block gets introduced. And so now P1 is going to be its previous. So this block is now the one that should be responsible for telling us whether or not P1 is free. And that's what we're doing here. We're setting the previous free of the right block, this guy with the arrow, to be whatever the value about P1's freedom is. So he's now going to tell us about P1's freedom. The problem is here when we set that is free. What happens is the drawing still reflects, right? So previous free is going to be pointing at P1 now. Okay? Previous free. What's going to happen now is when we set so this right block is intended to be free, right? Because when we partition, we want P1 to keep its information and we want to keep the right block as a free block. The problem is that doing this makes it so that, you know, the right block now needs to say, oh, I'm free. How does the right block say that it's free? Well, it tells its next guy to update its metadata. Because remember, if I want to know whether or not a block is free, I look at the next block and ask it, is the previous block free? And so now, this guy, right, it's telling its next neighbor to say like, oh, please update the metadata about me, right? So P2 sets its bit to say, whoever my previous is, right? So it's something like, let me modify the, here, our Excel, right? P2 is going to say something like, whoever my previous is, they are free, right? So P2 is going to tell us, whoever my previous is, they are free, right? Since P2 is the next block, like the right block, which is this guy that we want to create, the next block is P2. And so now P2 is saying that whoever my previous is, they are free. When we ask, is P1 free? What happens? Since we haven't updated the size of P1, P1 is going to say, well, I'm still this huge size. Who is my next? Well, my next is P2. So it goes asks P2, and P2 responds, whoever my previous is, they are free. So P1 believes itself to be free, despite this information being not intended for P1, but intended for the new block that's going to appear. So that is the bug, right? Because P1 is not free, but because of this modification, P2 is going to tell it that it is. If we were to change the size of P1 before doing this, so P1 now believes to be this size, the next of P1 is not going to be P2. It's going to be, you know, the new block. And thus we would obtain the correct information. But because we did that in that order and we hadn't set the size, we had that bug where like P2 tells you or sort of deceives you to think that you're free. The reason why we cannot set the size of P1 yet is because there's information in the footer. And the problem with information in the footer is whenever we set the size, right, the size it's written here at the beginning, so it overwrites whatever's there, and it overwrites whatever's at the footer. And the problem is the footer stores user data. So if we are to set the size of P1 first, we would get rid of the user data. So now we have to think about this more carefully on in which order we want to do things. So I hope the issue is clear now. So let's see, we set the size, we set the previous read. Yeah, I think like just to keep our sanity, right? Let's just create like variables that keep track of the state of what the state is before all these modifications happen, rather than relying on the order, because that's like genuinely really dangerous. So bk is, so here it's like is free block. It's gonna be equal to bk is free of block, right? And so that way, and in fact, we're gonna include a warning comment for our future selves. Try to store the important state you need in variables, because all of the, you know, block moving and the block manipulation changes temporarily metadata, like prev free of some block could temporarily be pointing at the wrong thing, right? So what we're going to do is we're going to save whether or not that block is free before we even start any sort of modification, and we're just going to use that variable, right? Block. This size we don't care about. We don't care about the set free. We don't really care about this. Then, yeah, we continue here, and then here we actually succeed. And I think that's going to be the solution. Perfect. So I think we can just make, and then we take a look at the memory inspector at the debugger and go at it again. Yeah, these are a little bit, these are like not even a little bit, these are very tricky. Very, very tricky. So malloc, yeah, I don't care about these. I care about this one only. Let me now move the camera a little bit up so that you guys can see the data. We initialize memory, we allocate. This we know it's correct because we saw it before. Let me now add the memory view for what we need to take a look at, which will be 0x1234567 whoa, 0x1234567 1005 A1 AD0. Perfect. And so now we have realloc, right? We enter realloc. We continue all the way over here, right? This is fine, this is fine, this is fine. We detect that we need to shrink. We enter partition if worth it. So remember, after the partition, we should still be seeing the this is, right? And the space after it can become whatever it wants, but the is like the end of the section we want to reallocate. So we continue, we continue, we continue. We evaluate, is this worthy of partitioning? And the answer is yes. So now we continue. And now we say, well, when we are shrinking, right, I want to know if the partition is worth it. But notice that we still have a problem. We still have a problem. The is got overridden, right? Am I tripping? Is this just not, let's see. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so the I at least. No. All of these should stay. So what is going on? Where? Okay, now it's something else, right? Now we're overriding the wrong thing. What? It's okay. Let's see what happens. So We run this, we enter, we step into the function. Edit this. I'm gonna call it heap. 1005 C1 80. There you go. Okay. Perfect. And so now, get a little smaller. There you go. So now we continue. We go here, no. Oh yeah. We allocate. We enter realloc. Let's see. We go through the sizes and all that stuff. And then we see that it's shrinking, right? We enter leftover block and we try to see what happens. So we see if it's worthy of partitioning. The answer is yes. So let's see what happens during partition. We calculate all of this stuff, right? Here we determine whether or not this is a free block, and the answer is not. It's not a free block. Yeah. So now we set the size of the right block, which should not interfere with the user data. We see that the is still there, right? Then we set the previous free of the right block, which should make this 40 which should make this 20 a 22. No, which should leave this 20 being a 20. Lady 1997, hello, welcome to the stream. And about 12 Ravens, thank you for following. Thank you for following. And same for Lady and to Dito BRJ81. But yeah, so here we set the previous free, we shouldn't change these 20, right? Indeed it doesn't, which is great. And when we set the free of the right block, that should change this 40 to a 42. And we should still see the is free block be false, right? Yeah, so is free block is still false, but this guy, sure, it changes and stuff, but that variable is still there. Thanks, how are you? Are you okay? Yes, I'm okay. Yeah, I'm fine, I'm fine. How are you, Lee? How are you? I'm trying to... my hair is behaving weirdly today. It does this thing. I don't know why it's doing that, but... Yeah. Anyways. So let's continue. And yeah. I don't know. So let's be away. What does that mean? Wait, what is away? But yeah. So let's continue here. Let's see. Oh, wait. We're entering the right section, right? So we're going to copy into the user info a new footer, whatever this thing is, which is the beginning of the heap, the size of an allocated block header, plus the size needed. Oh, of course, this is not... Dude, what are you... What am I doing? Oh my god, this needs a block here, right? From the beginning of the heap, travel to this block, skip its header, skip the amount of size that's needed, and then write the footer at the back of that, right? I mean, always be well. Great. Yeah. True. Let's go. So I think that was all. Okay, it was just us being stupid. I think it's better if I just separate that into like its own function. So first start of like, sort of new footer pointer. It's gonna be equal to whatever the new footer is about to be, which is this guy. And so now we just do new footer, then we set this thing to be over here. There you go, perfect. I know I'm covering some of the code with that. But yeah, I'm gonna move this here. There, I think that's way better. Um, so, of course, new footer pointer. And if we recompile, I think we're gonna be fine. And then see the magic happen. I don't know. Dude, at this point in time, we have to do like rituals. We have to do a dance to hope for this thing to work. Dude, anyways, I'm also learning programming and I'm glad I met you. I feel like you're an energetic person. Thank you. Yeah, yeah. So you can hang around if you want, learn about the memory allocator we're building. Go in and out of the stream however you want. And I'm glad you're also learning programming. Yeah. So it's I think many of us are learning too with these things, although there's a lot of experienced people in the chat too. Good, y'all. Yeah. So we're gonna test realloc, right? We do the allocations, we don't care about this, sure. We enter the realloc, and now we need to take a look at memory because memory is very important. C1, okay, this thing changed now. What is it now? It's 6-1 AD. Oh no. 6-1, 6-1. Whoa. 6-1. Huh? Oh, D60. There you go. Okay. That makes more sense. Okay. Then we chop this a little. Then we decrease it a little. There you go. So we run realloc. We go here, we go here, we go here, we go here, we go here. We try and stream every day. Yeah. I stream it every day at 7:15 a.m. Pacific time. So currently it's 8 a.m. So like 1 hour in the past, 1 hour and 30 minutes from now in the past, we start stream every day. So yeah. We partition of worth it, right? Oh shoot, wait. Did we just see it happen? Yeah, wait, the is still here. Yo, it worked. Let's go. So we didn't corrupt any of the user's information, right? Hello everybody, this is, and the is still here. Which means that we're in a good state, because then, oh shoot. Another error, question mark? Is this another error? uh, you. I think it is. I think it is. Yeah, right? No. How many blocks do we have here? We have only like... We have a very limited amount of blocks, right? Good, we will definitely come to see you. Oh, who's we? Oh, there's like multiple people. Yeah, thank you. And Ancient Slabs Dev 01, thank you for following, and same for Lord Sidious 66. Yo. But yeah, so am I... Huh? Are we like crazy? Crazy? I was crazy once. They put me in a room. A red room. A rubber room full of frets. Okay. Anyways, oh no, we're not crazy. No, that was going well. That was going well. Did what happened? Yeah, so we allocate, we write, we allocate. We enter the realloc and we write and reallocate. And we do anyways. Brother, what? Added, yeah. 0x 1 2 3 4 5 6 7 1 0 0 5 C9 AD 0. Perfect. So when we reallocate, it's taking so much time. We partition forth it. That should take the is back. That should take a look at this and say, no, this thing is not free. So then we skip it, we insert it, and then we return. Right? Yes. So you should be in good hands. Yay. And so now, pay attention. Because the biggest event in world history is about to happen. 21, this 21 over here, represents the free block that was left behind. And that guy is very important because this block ends here. So this block is free. But the next block is not. The next block is P2. So now the tiny bit, it looks like P1, a tiny bit of free block, and then P2, right? And so now what's going to happen is if we free P2, we expect P2 to merge with the little guy to create one huge free block, right? Resin Deskert. Well, I imagine it's Resin Desk RT, right? Debugging low level stuff. Wow. Yeah, we're taking a look at the memory inspector. It's like fun, but at the same time, it requires like too much detail, and I don't know if I'm able to handle that. Um, Lady, can I see what you made? Yeah, of course. We can take a look at the memory allocator once we solve all of the bugs that we have here. So remember, people, when we free P2, we should see this 20. Actually, not this 20. This 21 change to something like 63, 70, around that ballpark, if you add the headers and stuff. So, okay, I'm gonna give you an exact number. It should be, actually, I'm not going to give you, no, I am going to give you an exact number. It should be 63 plus the 8 bytes from the previous header. So 63 plus 8, and that's gonna be 11, so it's probably gonna be 6A. 6A. So let's pay attention to this. Once we transition here, 69. So why was it 69? Good enough. To be honest with you, like that seems good enough to me. Yeah. Why did I say 6A? Because I did 42 plus 21. Oh wait, but it shouldn't have been 20. Yeah. Okay, 21. So it should be 6A minus 2. So that would be 6. No. Yeah, 6A minus 2, which should be 68, plus 1, which should be 69. Yeah. Yo, we're so back. We are so back. Let's go. And so now everything should be free except for P1, right? And we should see the heap expand by a little, maybe. Yeah, probably by a little. So how much is 69 in hex? So how much is 17 hex? 7 times 6, sure, and then 2, 7. Okay, it's not enough to allocate that much. So I think the heap is gonna expand a little more. Yeah, to 232. It was 168 before, right? So 168 times 35%. Let me check it out on my cell phone so that I can, let's see. It's 6, how much was it? 168 times 1.35, that's 226. Yeah, that's about what the heap expanded by, so we're good to go. And then we return true after we copy all of this information. So we should see all of this getting overridden by this huge string. And indeed, 128 bytes, right? 128 bags, that's a lot of information. Not sure how we are going to fill that up with a single string and all an allocation. Bye. And that's exactly where it ends. Perfect. So it means that our memory allocator is working correctly. It's working the way it's intended to work. And we actually have a little free block over here. So we could technically just still use some more information. Um, Seems like it's working. Let's go. Okay, let me now read the chat because I wanted to finish everything here. Can I see what you made? LOL. Because 69. All right, Vicente. Okay. Okay. We have Lucky Door Zero. Yo, thank you for following, Lucky. Okay, okay. So, people. This is, if anything, a small step for us, but a huge step for us too, because nobody's gonna benefit from this memory allocator since it's since it's not at all professional, but you know, for the sake of learning, it's pretty good. Um, we have this branch. So the price that we're going to get is have a commit that describes the fix we just made. So we're gonna perform a fix on the realloc guy, and well, I'm just gonna call it like maybe not realloc. Well, yeah, sure, realloc. Uh, Bug in preview in partition block, bug in partition block where metadata would be used while in invalid state. Then we provide a better description of that, which is BK is free was being used before or like while in invalid state during a partition. Yeah. Let's just say like changed things around to what? Changed things around to what? To use a variable before changed things around to use a variable before what? To store the needed state before temporary invalid state was introduced. Perfect. And then we push. All right, let's go. Okay. Am auch nicht nennt. Immunent? I'm not sure how to pronounce your name. I'm so sorry. But welcome to the chat for the first time. This is how are you checking for correctness? That is a great question. Anyways, no. It's a great question because so yesterday we were having like a little bit of a crisis, right? We were descending to the 10th circle of hell, which it doesn't exist in Dante's Inferno because there's only 9 if I remember correctly. But this was number 10. This was the one that was hidden behind a wall and reserved for the biggest suffering of them all. Because we're trying to test the memory allocator, and the problem is that we wanted to test an implementation, but there is not like a good way to do that. And by that I mean like one way to verify whether or not a memory allocator is working correctly is to check every single byte is in the position it should be. The problem with that is if we ever change the memory allocator, the bytes in memory may just change around a little. The test is going to flag that as completely incorrect, despite the whole overall correctness still being preserved. So we cannot compare byte by byte. What we tried to do was do something like, you know, maybe I can describe an overall state of the heap. I can say there is one block of this size, then it should be followed by a block of this size, and then it should be followed by a block of this size, and so on and so on and so on. But then we rapidly encountered a problem where the memory allocator is able to decide whether or not it wants to modify the size that we provide to it. So if I say allocate 23 bytes, the memory allocator may allocate 24 instead, right? And so we, as the testers, we don't really know the exact size that the block is going to have. Or in this case, we do because we wrote the code. But if that rule ever changes, then the test is going to be completely bogus, and then it's going to make no sense. So, you know, what we do know are bounds on the size. We know that the size is at least what we told it, and at most this much. And so we said, all right, let's test it that way. Instead of describing each block in the exact size, let's test each block in like the boundary on its size. The problem was coalescing. So when you have a block that's freed and to its size something that's allocated, but then this allocated guy, you free it, then you coalesce those two blocks to create one big free block. And the problem with that is that now you need to perform calculations on, okay, how big does that block need to be? And how do the bounds change when two blocks coalesce? That is still doable. The problem is the expansion of the heap. So when we expand the heap, we have a heuristic that says, that behaves sort of like a vector, right? Whenever you fill up a vector and then you try to push new element into it, the vector doesn't just expand by one, it expands by double its size. And that is a heuristic to keep sort of the operation of pushback to be O of one amortized, right? So a similar thing we're doing with the heap, where we just want to save, in a way, syscalls, right? Because syscalls are like a little expensive. So if we can save system calls, then that's good. So we perform an optimization like that, which means that at a given point in time, the heap could expand by whatever factor we specified. And if that factor ever changes, the size of the free block at the end of things, it's going to be bigger, smaller. We don't know. And so we cannot test that. We cannot test the size, because then if a block is freed next to this free block that happened with the heap expanding, then it's going to coalesce with it. And when we try to measure its size, we're not going to know, because we don't know by how much the heap expanded. And so we cannot test it that way. So I was just so frustrated yesterday that I just said, all right, guys, let's just not take a look at this today. Let's leave it for tomorrow. And guess what day it is today? Today is the tomorrow of yesterday. So we have to figure out, how do we want to test the correctness of things? What is the right level of granularity to look at things? Because we could say, let's test the memory allocator in a general way. Let's just see that the information is not lost. Yes, but what happens if part of your code is being really inefficient by giving this huge block to you when you only need to use the first 3 bytes, for example? There's a way in which you should be able to say, ooh, this is happening and this shouldn't happen. There's also a way in which you should be able to check, am I coalescing the blocks, right? Are the blocks actually merging with each other? And that is something that is really difficult to capture without being a little bit more granular. So we're trying to find a way to test things. Like here we were fixing some bugs that we had found, and now we're going to proceed to try and test things, and to, rather than proceed to test things, find the correct way to test things. That would be my way to say it. Bunchar, thank you for following. Let's go. So yeah, and to respond to Lady 1997, which I haven't forgotten about you, our code looks something like this. So basically, we are implementing the 3 main functions that relate to memory allocation. Malloc, which we have called nalloc with an N, which allocates memory for the programmer. Then we have mmFree, which we just called it this to distinguish it from the actual free, which is a reserved whatever from C. And yeah, we do all this stuff. And then we do realloc. Realloc allows you to reallocate, to move information from one block to a block of a bigger or shorter size. And thus, this is what we get, right? And that's it. So we're just building those main functions, and you've been seeing how they work. We've tested them to a degree where we are relatively confident they work, but not completely sure. And that's what the stream of today is going to be about, right? How do we guarantee, or how do we not guarantee, because you can never guarantee correctness unless you use an actual, proof, languages like Daphne, Rock, etc. Um, so formal verification. There you go. That's the name that I was looking for. Unless you use formal verification, we will never be sure if there's a bug. But like at least increase our degree of confidence, right? Should it be mmalloc? Well, not really. I wanted to call it nalloc just because it's like the new malloc, not malloc. You know, not that impressive malloc. I have no idea, but nalloc is just there. And then these guys will. I guess they should indeed be called N free. Like, I just this is just some random name that we did. So let me read this. Is your allocator deterministic given the same calls of allocations, deallocations, reallocations? Yes. The allocator is deterministic with respect to those calls. Like it behaves the same. Um maybe you can fuzz it somehow. Oh, hello, Fambier. So Vicente Alencar, yeah, that was something that we were considering last time. The thing is, I have not much experience with a memory fuzzer, and the concept of a memory fuzzer applied to this allocator um, is a little bit confusing. Like maybe you guys have a better idea on how we should apply it, but from what I understand, right, a fuzzer is very good for defensive programming, right? Where you need to have an input of a certain instruction, you need to check that things are being correct. So for example, if the user is giving you or uploading a file or is giving you a string, a fuzzer would be amazing to, to try and test how defensive you are and if you're actually checking the things you should be checking. In our memory allocator, we don't really have, that need for defensive programming. We more or less have like, we expect the program to do a specific set of things. Like, so we want to check that like the blocks are coalesced, right? And that is more like an action rather than something that you can fuzz out of things. Like, I'm not sure about it, right? But from what I understand about a memory fuzzer, which is almost nothing, it's just like, flipping random bits in memory and so on and see what happens. And in our case, that wouldn't be like very helpful, right? Because the things we need to test are a little different, right? They're not on the defensive side at all. They're more on the, is this thing actually merging the blocks? Which a memory fuzzer wouldn't be very helpful at, right? Because it wouldn't really tell you much, like how, did the blocks merge or not? And, you can also not fuzz the headers or the footers because the whole thing about the allocator is that it relies on the headers and footers being actually correct. We could use a fuzzer when we are doing, if we ever want to, the logic about what happens if the user overrides the footer or if it overrides the header. Right? What if they use the pointer for something malicious? In that scenario, we can, because then we use a fuzzer to modify a bunch of stuff in memory, and then we need to have a heap checker that says, is everything in place? Right? In that case, yes, but for the correctness itself of the allocator, I find it really difficult. I was used to Visual Studio at first, which was super easy, but I moved to Sea Lion. Big mistake. Anyways, when I started Linux Maxing, which uses CMake, but I skipped all that learning part and vibed it out. Fine. Don't do that. But then Claude got stuck and my really shatter. There you go, bro. anyways. Input would be some encoding of the order of instructions. You mean for the fuzzer in some sort of sense? So yes, in the order of instructions. So like, my problem is not find like, because a way to test the memory allocator would be to, you know, would be to use this memory allocator and attach it to an already existing program and let it run and see what happens. My problem is like, how do we actually check that the memory allocator is doing the right stuff, right? So like, how do I peek into the state of the memory allocator and check, yes, this is correct? if you check, once again, it's the same thing over and over. If you check byte by byte, then whenever the memory allocator changes a single thing, all of your tests are gonna be on. So you cannot do that in order to check how it behaves. If you want to check block by block and their sizes, then what I said doesn't, like, because of what I said doesn't work, because the memory allocator is free to change the sizes a little so that it is 8-byte aligned. If you check by bounds of the sizes, then it doesn't work because of the heap expanding and the fact that you don't know all that. So, like, how do you check? What do you check? Right? So currently, the only way I see this being possible, like some sort of testing for a memory allocator, is logging, where we just log what happens. We log this thing happened, right? So, and in fact, we have introduced logging, if I remember correctly. It's in a different branch, but let me actually check what branch it was. Yeah, test/logging. We were adding some logs yesterday. This is a little outdated, but see, it's like malloc. Request for D bytes suffice with block D, right? Like, is this right? Check some. Oh wait, do you hate Silian? Not really. I just, I don't know. It's just like, Visual VS Code already has everything you need. but yeah. Um, checksum the data. Yeah, so checksumming the data would be useful, but like in the case where you're trying to be defensive, right? Where you're saying like, oh, what happens if the user overrides my header? Then I would want to checksum the data, right? But in the case of the allocator, like, checksumming doesn't make much sense, at least to check for the correctness. It wasn't Sea Lion's mistake. It was my skipping fundamentals because I want to. I see it. Yeah, for sure, for sure. I see Black Deep. I'm mildly impressed. You got VS Code configured to debug C code. Okay, brother. Do not hate on VS Code that way. VS Code is great, right? I'm probably in the future, 2 years from now, gonna be like, guys, NeoVim is amazing. VS Code is super slow, which I actually think right now, like VS Code is kind of slow, especially with C. But for now, VS Code is a friend of ours. VS Code, very pretty. But yeah, okay, it's capable, but I have no idea. Okay, yeah, no, that's valid. That's valid. Um, It's not trivial for sure. Yeah, yeah, I agree. Rudy fan, welcome back. It's going good. How about you? Mm, okay. So I think the way we're going to do these things is exactly that. We just check the logs, right? So we're like, oh, right. I don't know how big this block is, but I know that this block should have been used to suffice that request, or something like that, right? Um, yeah. So I don't know. I don't know. Um, okay, let's think about this. Independent of what happens, right? Because we want to implement coalescing, we know that the approach with the header and the footer and all of that should be there. Um, okay. So what I'm thinking right now is there's going to be multiple things that we're going to do. Let me go to main and let me merge the branch with the logging so that we have logging now. Oh, we have a merge conflict. Where? Here. Oh yeah, no, we want to accept the current change. Yeah, that's dangerous if we don't. Perfect. Then commit the result. I think we're fine. Yeah. Get that dot with. Oh wait. What happened to do? Oh, okay. Git commit -m Sure, this is just merge with tests slash logging. Perfect. Okay, let me push this. So, let me see. Let me see. Idea of using reference implementation for tests are good. Uh, when you okay, so you mean like we compare this to malloc, right? Um, but then like how do we compare them, right? What does it mean to compare this to malloc? That it's using the same blocks, that it's using the same amount of memory, like how? Like that is my thing. Like what do you even compare? Is my question. Right? What do you even compare? It's not like how to test. Well, I guess it's how to test it, but like how do you compare? Right? What characteristics of our allocator do you grab and that we care about? You cannot care about the place of the blocks in memory. You cannot care about the size of the blocks in memory. You cannot care about the size of the heap. You cannot care. So at the end, what can you care about to put in a test, right? So it is not care about, right? What can you rely on to compare? It's what I mean. If you change the allocator, then update the tests. Yeah, but I suppose if you're iterating quickly, then it could be painful and can wait until it's more stable. Yeah. Like a macro alloc that maybe nalloc or malloc and assert outputs are the same. Test programs output that aggregates some data. Yeah, so comparing the two, right? Assert that the outputs are the same. Like, to what extent? Because the only thing we can check is that the data is still there. We cannot check if the blocks are the size they should be. We cannot check if they coalesce. We cannot check if the heap is the size it should be. We cannot check basically anything, right? And so all we can do is like test that the user data is still there, which we can do, but it feels like two cores of a test to tell you something significant, right? Suppose that all of a sudden I remove the ability of blocks to coalesce, the user's data would still be there, right? Because the heap would just expand unnecessarily, but the user data is still there. I would never notice that the blocks are not coalescing anymore. So yeah, and like how do we know if the output of malloc is correct? Well, comparing it to malloc, yes, but like these are memory allocators that behave very differently. They put the blocks somewhere else. They merge blocks, they etc. 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 So yeah, like I think our only solution is the logging part, where we say, okay, when I call realloc, I need to expand the block. Right? Like that's all I need to know. And just take a look at the logs and say, this sequence of logs should occur, right? Independent of what they are. Yeah. So log debugging is what we were sort of seeing was the better approach, or rather than better, the only approach, the reasonable approach. And that's why we had the test slash logging branch, where we were adding a bunch of logs. So yeah. Let's also do the following. So one thing that I also want to do is we want to add a bunch of asserts. So go through the code and at every point in time, see what things we can assert and then just add a bunch of them. Add like thousands of asserts, and that way we also detect whether something's going wrong. I feel that's also a little reasonable. So yeah. Okay. Ba-da-ba-da-ba-da-ba-da-ba-da-ba. If you could rerun with malloc and the logs match, then it's correct. I think we're going to do the log debugging. I don't think we can compare it to malloc. And the reason for that is that like malloc may make different decisions, right? It's possible that when I expand the heap, malloc decides to expand the heap, but like by a different amount. or they decide to not merge these two blocks because they're too small while I do merge them, right? And so on and so on. Like this is not an exact copy of malloc. Um, because we didn't, at least I didn't want to take a look at the malloc implementation because then we would be biased. We designed this from scratch. So there are decisions that as we started building the project branched out of what malloc actually does. And I don't know which ones they are. So I don't think we can compare them to malloc. I think we can just log the things, verify that the output is like correct, and then just be like, yeah, this classifies as a test. And we just, engrave it and hard code it. I mean, from a high level, not inner details. But then the high level would be allocated this, free this, allocated these, free this. Which I guess, I mean, we would have to find, what things we want to log in order for that to happen. But yeah, it's definitely not impossible. So we'll see, we'll see. So let's first do the asserts and then we're gonna do the logs, okay? So let's take a look at this. So block of a free header, right? Allocate the free this and check contents. Yeah. So it would be too high level perhaps, but it seems to be the only thing we can do. Yeah. So what we have here is this. We have a block free header, right? And then we're going to. So this function would need to assert, for example. It's good if we assert that, the thing that you're actually giving me is not a null heap pointer, right? Here we can see that, please don't modify the footer of a block that's null. In size, the same thing happens, right? In prev free, we need to check the same thing. Here we check the same thing. For set size, we also, check the same thing. Perfect. Block on the left, the same thing, set left. Yes, this is fine, this is fine, this is fine, this is fine. To set the color, we do have a special case with that. That is free. We check that, set is free is there. Okay. When we're talking about the next block, we also want to check that, whatever we're doing, we're not trying to get the next block of a null heap pointer. That's interesting. And also, we want to check that whatever this block is a block that lives within our heap, right? So I guess we can create. I'm going to create this series of functions that I'm going to call, assertions. Not sure how else to call this section, but it's going to check whether or not things are correct. So bool is valid block. So what do I mean by is valid block? Is valid block, and I think I'm gonna write it in all caps, is valid block, just to know that this is not a normal function. You're gonna pass me a block, and then I'm gonna have to verify a bunch of stuff about this block. So whenever a block is passed, I need to assert that it is a valid block. So first thing is we're going to return, is this block different from a null heap pointer, right? If it's a valid block, it should be a null heap pointer. If it's a valid block, it should live within my heap, right? So what does it mean to live within my heap? It means that the last byte of this block is inside the heap. Let me read. Ajob 00693K. How do you learn this stuff? Oh, thank you for joining the stream. And I mean, we learn just by throwing ourselves into the void and trying to find a way to get out. Like, we started the series, had not implemented a memory allocator before, and so we just went with it, and we looked up on Google, how does a memory allocator work? What are the concepts that you need to know? and then just started implementing one. So yeah. When we need to take a look at this block, right, we need to check that it's within my heap. And the way we do that is when we take a look at the block, right, and then we skip its header, and then we skip the size that it has, we get to a point that is smaller than the size of the heap, right? Let me see. Is it smaller or? Oh, okay. This was Landos in the first byte after the block, so -1. There you go. So we check that it's within the heap. And okay, nice, bro. I like how you talk through every approach. Thank you. I hope that's helpful, especially when it comes to, because even then, because talking out loud allows you to detect bugs, but we've had like thousands of bugs. It's really bad, but like it's okay. It's okay. So what else can we check about a block to see that it's valid? Well, we want to check that whatever the header says the size is equal to whatever the footer says the size is, right? We only do that so, like, you know, if the block is free, if the block is free, if the block is free, then we're going to check that its header is that its header is correct and corresponds with its size. There you go. And so we enter the header of the block, which is gonna be a little bit, you know, BK header or BK free header of my block, and then its size. Or well, I guess, okay. We check that the BK size of the block is equal to the block's footer, BK footer, and then whatever that footer is saying the size is. So we check both. Brother, what happened? Hello? I think we just need to enclose this in parentheses. Is that enough? Call to undeclared function BK footer. Oh. Yeah, whatever. Let's move this section down below. So over here. Block neighbors and everything. Yeah. So there you go. Okay, perfect. And Kuyok, hello. Welcome to the chat. I see you follow. Thank you very much. And same for Ajoub 00693K. Thank you very much, guys. And yeah, we're here trying to test the memory allocator. We're checking its correctness. So not only do we need to check that the block is free, and when it's free, we check that the header and the footer coincide. If it's allocated, then remember that we may not have information in the footer, so there's nothing to check here, and that's why I just return true. What else can we check about a block to see that, you know, it is indeed correct? Do we have, I think we have a general max heap size. Yeah, max heap. Max heap is the size of, yeah. So I think we're good to go. I think this is the, you know, as many things that we can check about a block. Right. Without knowing its contents. I think that's more than enough. Perfect. And so now what we do is instead of asserting all of these things all the time, we can simply just, let me, actually no. So, oh, wait, that's interesting because then it means that to call these functions, I need to do is valid block. Okay, we're just gonna assume that the member variables are correct because they're very simple, right? Grab from the header, the parent, and so on. And we're gonna use this is valid block inside these other functions, right? So partition block is an example, right? Where we not only assert that we have the size needed, but we also assert that whatever block you're passing me is valid. Right, so we're gonna assert that. We're also going to assert, let's see. So there's gonna be a bunch of assertions. By the end of this function, we need to know that the block that we passed at the beginning is still valid, and that the new block that we're going to pass is also still valid. By the end of it, both of them should be completely nice, right? Perfect. So now here, partition if worth it, right? For partition if worth it, we want to assert that the block that you're passing me is a valid block. Is a valid block. And what else do we want to assert? We want to assert that I guess, hey guys, would you guys kill me if we were to implement a macro called defer, and then we do all the asserts that we need before exiting the function? Right, because like I would need to check that at the beginning the block is valid, and that after coming out of the function, the block is still valid. So we would do something like this, right? It's very similar to Golang's defer, and we can implement that with macros, but you know it's a little bit of like black magic. I don't remember how to do it. I know it's possible because I've done it before. Are we against this? Are we against this? Because it's not idiomatic, right? Like it's not a thing that C is supposed to do. But like, you know, like it would be very beneficial because there's two returns here. So I don't want to include the assert here and then the assert here. In the meantime, let's continue with the other functions and just let me know your opinion. Here we need to assert also that both blocks are valid. So it's valid block, then block 1, ouch, and is valid block, and then block 2. Perfect. Okay. And by the end, we would also need to check that. So defer the fact that these two blocks are still valid. Is there anything else we need to check? I'm not a fan of defer. It just obfuscates control flow. Yeah. Yeah, but it's, you know, it's for the tests. It's for the tests. I'm just writing defer to know that this should be at the end of the function. Yeah, so okay, so no defer. Okay, that's fine. We can do it with no defer. There's a reason why I asked, and it's because I see the arguments for both sides, so I'm unsure of which one to use. So let's just do this. Assert that it's valid block. So everything. And then over here, we now have to put this in two places. So I'm gonna separate them by a little bit. Assert that the block is valid, and then here the same. Assert that the block is valid. Great. And then we continue, right? It is a little confusing to have so many asserts. Should we just include like, a little line here and then a little line here to denote like where the function code actually is? Because I feel this is kind of nice. Um, I don't know. It's the same reason I don't like exceptions. Yeah, makes sense. Sure, like I see the point. I see the point. So we're asserting everything is valid and stuff like that. Perfect. Blah 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 blah. Call S blocks. When we initialize the memory manager, there's nothing to do. Lazy initialization. Perfect. So we arbitrate block and then the no heap pointer. We add padding, the ghost node size. We do this. Other parts of the program rely on the ghost node being the first node in terms of heap arrangement. So it's very important that we assert that. Assert. Well, I mean, there's nothing to assert here, right? Because like we set it to be the beginning of the heap. Uh, so like, maybe we can do it here. And we can say like assert that every single time arbitrary.block equals the padding, but we don't have access to padding. I think we can just make padding a global variable so that we can access it, because it's getting a little annoying to have to not know where the heap is. So if we do un32t, then we say padding, that's gonna be like way better. Way better, because now we can just set padding to whatever to what it should be, and everybody knows where the heap starts. Because up until this point, we've been obscuring that fact. We've been just not telling anyone where the heap starts. We just make them trust. So yeah, we have the heap with the padding and all of that. Oh, sorry, that shouldn't have been. Should have been this, right? Can I have 10 IQ? Brother, what 10 IQ? Like, what do you mean? Is it Q like Oh, you mean like? What do you mean? Oh, thank you, thank you for the compliment, but no, I mean, this has been a project that's taken a long time, and it has been the project, the product of a lot of thinking with everyone here in the chat. So I think you should ask everyone, But no, I mean, if you're watching the stream, then you're pretty smart too, because very few people want to see the implementation of a memory allocator. Anyways, so here what we have, let's see, we have this lazy initialization. We need to assert that at every point in time this happens, right? That this is true. What else do we need to assert? We also need to assert that the ghost node is a valid block, but well, not really, right? What else can we assert? The size cannot be negative because it's size t. I think this is it, right? This is all we need to check. Then we do size is equal to this. And then we say, okay, allocating n many bytes. Are you not using an AI for practicing purpose? Yes, for the sake of learning, right? We want to learn, and we actually want to understand a memory allocator. So yeah, no AI for that reason. Yeah, so we have here this free block, which fine. It is important that Well, actually, we don't know if the free block is valid because it could be null. That signifies that there wasn't a block that we found. So when we remove from the red black tree, okay, I see. And then we set it to be free. I just saw you have the whole series on YouTube. I might watch and code. That's pretty good. I mean, the videos are like extremely long. I really long because like the streams go like until late. I have it on YouTube just for the sake of preserving, right? So that like you can see the path there as we went through, starting from like an empty file. Um, yeah, the videos don't do really well, and it's not my intention for them to do well. They're there for like archive purposes and to take a look at them back in the future. But yeah, glad you found the YouTube channel. Um, let's see. If there's a free block, right? If we can remove this from the red black tree. We can set it to be free. And so I think one thing to assert right here would be something like this is a valid block. Right, like at this point in time, we know this is a valid block. What else do we know at this point in time? We set it to be free. So okay, guys, I have a bit of a question. Those of you who maybe have more experience with development, I do want to include the asserts, right? The problem I'm encountering, it's like I don't want to fill the entire code with them so that it becomes like impossible to read. So an example is, we could include an assert here that says is valid block. And then whatever that function gave me back is an actual block. So I could do something like this. The thing is, I already know that this partition of worth function gives me some sort of valid block because the partition of worth function returns like asserts just that, right? And so, like, should I just put it in the preconditions like this function provides you a valid block, or should I put it on both sides despite it being completely redundant? I know it's more secure on both sides, but then the code starts being like 4 asserts for every line, which I guess it's safe, yes, but like, is it what we want? Oh, and that is like my current conundrum. Like, do we really want that to be the case? But yeah, anyways. Okay, so let me know in the chat if you guys have an opinion about that. One thing that I think we need to do is here we're returning back from malloc. So we're going to assert a couple of things. First, that the block that we're giving back to the user is an actual block, right? It's valid. We're also going to assert that whenever we give it to them, it is a block that's marked as allocated. So this block is not free. What else can we assert about something we give to the user? We can assert that the block is free, that it has whatever it needs, that... Well, we can assert that the size that we're providing is at least as much as the user specified. So the size of this block is greater or equal to whatever the size the user asked for. What else can we assert? What else can we assert? That it's a valid block, that it's not free, that it has the size that it needs to have. That's kind of it, right? I feel that's all we need. So now we continue, right? Is the last block free? Then last block recyclable, the last block free. Then we need to, over here, right, assert that the last block is a valid block, right? So whatever we obtain from that last block is valid. We also need to assert that it is indeed the last block. So we assert that the next block from this is equal to no heap pointer. This is indeed the last block. Yeah. So I think we're good. And then we remove. Okay, perfect. If there is no free block, go to expansion size. If there is no free block, we calculate the expansion size. And there's something we need to assert about that expansion size. Right. The expansion size. Assert that the expansion size is like. Actually, no. There's nothing we can assert about it. We don't know which one of these is gonna pick. The response here, we have this, right? Heap expanded by this much. If the last block is free, we set its size to be whatever this is. Then we convert the expanded area into a block, the last block by definition. I guess one thing we can do here is when we do the setters, when we say like set pref free, we assert that like, the other function is able to read exactly what it's intended to read. So that the pref free is actually equal to pref free, right? So assert that after we make this change, this guy is able to read it. I feel that's reasonable enough. When we set the size, for example, we're gonna assert that the block size of block is equal to size, right? And when we set the left, we're gonna assert that the left that you read from that other function is actually the left that I put in there. We also want to assert that, oh wait, no, before the return. Oh, this is a getter. So now we want to assert that, the bk write function can actually read what you wrote. So then write, so equals right. Perfect. We want to assert, not here, in the next one. We want to assert that the parent function is able to read what you wrote. And so that way I'm able to judge whether or not we're a good header or a bad header. Getter. Then that this is equal to the parent, right? So now we got this guy over here. So we assert that the block color is indeed what we intend it to be. Sorry. Perfect. Finally, here in the set is free, we want to say assert that, bk is free is able to read whatever you just did. Or my block is the same as is free. Perfect. Oh yeah. No. Okay. And then finally, if we assert in here, that's right after it, that the bk is free of my block is equal to is free. Perfect. So I think use the font declared identifier. Oh, okay. The Z++ extension is just a little slow. Next block, pref block Yeah, that's completely fine. Perfect. And then is valid block. Okay, perfect. So now we can go back to where we were. We're taking a look at malloc, and now we say all of these lines, yeah? If the last block is free, do this. If the last block is free, then check that whatever the last block is indeed a valid block, that it is indeed the last block. Calculate the recyclable space, and then if there is no free block in our allocator, I saw a message in chat. Give me 1 second. Just want to make sure that I don't lose the thread here. If there is no free block, then we do this, right? And then we expand it. We set the size to something. We're good with that. We convert the expanded area into a block, the last block by definition. So here it's very important that we make it so that, we assert that, first of all, this is a valid block at the end of this. It's one thing. And then we can also assert that this is indeed the last block. Okay, perfect. New message from Pane di Altamura. Bro, this is the most cool things I've ever seen. Yo, let's go. Perfect. How'd you find it cool? But yeah, feel free to hang out, contribute any ideas, anything you think, or any questions you have. We're developing the memory allocator, and we are now checking for correctness, sort of making assertions through the code about the things that we believe are correct. Yeah, so that's so that everything crashes if these assumptions are never true. So yeah, okay. Block set is free, the last block to false. Then we have a leftover block from the partition of worth it. And then after this, we can assert that this guy is indeed a valid block, right? It's a valid block, the leftover block. What else can we assert about it? Not much, right? Perfect. And finally here, when we return, we need to perform the same checks. Perfect. Great. But now instead of free block, it's got to be, oh, sorry. Sorry. I think it's last block. Last block is the one we are checking for. Great. Okay, awesome. So that was nalloc. Then we have free. So I'm just gonna commit this. Get a dot. Git commit dash m. How do we label this? Do we call it test? Like, because we're not adding tests, but we're adding assertions. So is it a chore or a test? Wait. Control C. Yeah. Okay. I'm not sure which one it is. I feel like I'm gonna do a. I'll do test. Test malloc. Malloc actually. Test malloc to be. What should it be? Test malloc. Add assertions to malloc. Oh, that's fine. Great. So now we say mm3, right? We need to reinstate metadata. Okay, perfect. So at the beginning of things, right, I need to assert something about the pointer that you give me. I need to assert that this block is a valid block, right? I also need to assert that this block is not free. And what else do we need to assert about that block? I think only those two, right? That it is a valid block, it's a block that actually exists, and it's a block that is free. Also, I don't think I have that panel open. Oh wait, the camera is on the way. There you go. Becoming a computer engineer is my dream, but I'm not very good at math or physics. I hope to improve and reach a high level in this field. Let's go, yo! I mean, if you're taking a look at the stream, that's a good, a good mindset. Maybe uh, if you want to become a computer engineer, you know, bath yourself with projects and interesting things. You don't need to be like extremely good at physics or extremely good at math. If you are, that's better. And I mean, I have to hope you'll be able to be really good at these fields. Um, everything is possible when you set your mind to it and when you have the discipline. It is the only thing you should have in mind. Yeah, this sums up. Hi, welcome to the chat. And by the way, Pane de Altamura, great. It's good to have you here. And yeah, let us know. Like, are you working on things right now? What are you looking at? And this sums up. Hello. Yeah. So currently here in free, right? We need to check that this is a valid block. We need to check that this block is free. Um, Not much else, right? Oh, Control Byte, thank you for following. Yo. But yeah. So we set the size. We set it to be free. Right. Um so it hasn't been overridden. Okay. Coalescing the order matters. So this block is equal to the next block. You got spinning. I'm still standing. Better than I ever will. Looking like a true survivor. Okay. Pref block. I think this is a better organization of things, right? Where we have both of them be there, and then we change this guy to just not exist anymore. And we just say, well, you brother, previous block is different from a no heap pointer, and is that previous block free? And then pre-block. Great. So now we have it. Now we coalesce the blocks of the block. I guess there's also something we can check here on coalesce blocks. We not only assert that the two blocks are valid, which actually I'm not sure why I'm asserting this. I need to assert only that. We also need to assert that, the size of block 1 is greater or equal to the size of the two of them combined. But I would need a variable for this. So I would say unit32 OG size 1, and that's equal to the size of block 1, and then OG size 2, which is equal to the block size of block 2. And then here I check that the size of them is greater or equal to the OG size 1 plus the OG size 2. That's something we also need to check. What else do we need to check? So I think this is fine. And then over here inside of free, we're going to do, okay, so we have the P block, yeah, blah, 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 blah. We coalesce these blocks. We do this, anyways. By the end of it, when free occurs, we need to assert that what? So we need to assert that the block is free, right? Block is free of block is true. So we just put it there. Need to assert that that's true. And we also need to do what? So we assert that that's true, and we assert... Oh yeah, we assert that this thing indeed coalesced with other things. So we say that the block that's next to you, so either two things. So, ooh, these things seems to be not massive battery. I don't know why. don't know why. I got these feelings, yeah, I just can't seem to get away from. All right. So what can we assert? So we assert that whenever something is freed, the thing is like a conglomeration of like, it's like a big mass that merged with whatever was to its right and its left. So now we assert that the next block to you, either the next block is a no heap pointer, or that guy is not free. Right. So either you merged with it. So either right. If I freed a block, I expect it to merge with anything that's on its sides. So it's either the case that if you merge with everything, the thing to your right is not free, or it just doesn't exist. So that's what we're doing here. We're saying, well, either you are a no heap pointer, like the next block is a no heap pointer, or you just, it doesn't exist. Right? Or it's not free. Sorry. BK is free next block. And then we do the exact same thing, but for the left. So instead of next block, we just do prep block. And that way we can assert that we have at least, coalesced with things on our sides. What else do we need to do? So, Alexander Ravenscroft. Thank you for following. Yo, let's go. And yeah, single control byte. Here we are going to enter realloc now. So for realloc, we need to assert that whatever block we want to realloc is a valid block. So is valid block the block that you passed to me. I also want to assert, what else? What do we want to assert? I am not sure. I think that's everything we can assert for now. Then we have some space needed. Here, when we're shrinking, right? What can we say about shrinking a given block? Right, okay, we're going to say, wait, I want to check. Does partition block assert that the size needed is greater than 16? Yes. And does partition worth it make it the max of, yeah. Okay, perfect. Yoo-hoo. Yes, we're fine. Okay, well, actually, no, we're not fine. So in our to-do list, let's put get rid of magic numbers, because we have a lot of us, a lot of those. So I think I can just do this. So we already added the logs. That's fine. We're currently adding the bunch of asserts. The heap checker, I think it's something we may delay, right? Delayed. These guys. I feel like a bit of postponed. Anyways, so we're over here. We're on realloc, and well, I guess that before actually introducing the realloc things, let's just commit this. Right? Git add dot git commit dash m, and then we say test for free, and then we say add assertions, and then we push. Perfect. So now we continue. Now we continue on a journey. For realloc, we need to take a look at the space needed. Right. Sure. Then when we shrink, what can we assert? We can assert that That is true. We assert that the leftover block is a valid block, but that one we know about, right? I think we check that. Yes, perfect. But I guess, yeah, we assert whether or not you're a valid block. Whatever you've given me. Block. The space needed is this, and then I say, well, if the block size of the block is this, then we want what? So if the leftover block is different from a null heap pointer, and then if the out block is different from a null heap pointer and the block is free, so if the leftover block is different from a null heap pointer, we coalesce the blocks. Okay, I think not much to to have here. Over here we do need some assertions. So when we realloc, we need to know that the block that would be given back to the user is indeed correct. We also need to know that the block that we're giving back is not free. And what else do we need to check? I think Nalloc checked a third thing, which I don't remember what it was. That the size is greater or equal to the size, yeah. That's a great assertion to do. Include, right? Because size of the block is greater or equal to size. Perfect. So now, which I guess it's also something we can check while we perform a partition. So once we perform a partition, we make sure that whatever we return not only is a valid block, but it's also what we expect it to be. That its size is greater or equal to the size they told you was needed. Perfect. Okay. So now we do this, right? We shrink and etc. Then we expand. So on expansion with the right, and we merge the two of them together, coalesce the blocks, we partition if it's necessary, and then we return. And when we return, we need to check the same things that we've been checking. So we need to check that it is still a valid block. It is a free block. It's not a free block, sorry. And its size corresponds to the request. So perfect. Finally, if we merge with the left, we need to get, the previous size. So, yeah, I think it's fine. Our previous size, we merge the two together. We copy the user's information. Okay, so when we merge the two together, what do we need to check? So I guess that here, right, there are a couple of things we need to assert. And we need to assert that the previous block is a valid block. And I think we need to do the same thing over here, right? We need to check and make sure that the next block is a valid block. Perfect. And so now, what we have here is not much, right? Because we put this thing in, yeah. So here when we do p block, we remove from the red black tree, we coalesce the blocks, we set its free to false. We copy the user's info. So maybe we can check that the user's info is the same, although that seems to be out of our hands because then we need to create like a variable and store the user's information there and then do everything again and again. I think that's going to be left for the actual tests. Checking the integrity of the data should be part of the tests. For now, we're just asserting the normal things. So partition if necessary, right? We partition this guy, we check we need to coalesce with the right block. If the block is free for n block, remove it, we set it's free, we coalesce the blocks. Wait, why are we setting this to free? What does this have to do with anything? Why is that here? That should not be there, right? So what we're doing is we're reallocating, right? And we are in the case where we merge with the left. So we copy all of our information to the left. Then we see, is this block too big? So we get the leftover in case it is too big. And so now we want to free this leftover. What we do is we check that the next block is free. We remove it from the red black tree, right? Then we set the next block to be free. See how sneaky this is. This is like extremely sneaky. Dude, we don't need to even do this, right? And then we coalesce the blocks if we see that the two are compatible. And then we go out and then we set it free. Yeah. What was that line? Why was that there? It's not supposed to be there. That's interesting. Okay, I think the assertions would have caught it. So I'm going to comment this. Just see. Well, actually, no. Let's just delete it. Set it to be free, the leftover block, of course, and then we insert it back into the red black tree. That's awesome. And then here, since this is, again, realloc, we need to make the same checks that we did before. That the thing we provide to the user is a valid block, that it is no longer free, and that its size satisfies the request. Right, so independent of what it is. And it's not block in this scenario, it's people, what we provide to the user. Perfect. Now, here we're going to check all the things. So here I'm going to assert first that p block is valid. I'm also going to assert that, the next block is valid. So previous block and next block are both valid. Then what else do we need to do? So this is the case where we need to merge with both the left and the right. And so we perform basically the same asserts as we did here, where it is only just checked if it's valid, and then not much else. So remove it here, coalesce the blocks, copy all of the data, right, and then check the post conditions, if you will. Please don't go, Ali Joy. Okay, assert that it's a valid block, assert everything, and then there you go. Okay, if nothing worked, we just do the usual. So by the usual, we mean these guys. So we just assert the usual stuff. That is, whatever we're giving to the user is not, is a valid block. Well, I guess there's not much need to do this because we already know that the nalloc and the free work correctly. So that's going to be fine, right? Okay. I think those are all of the asserts that we want. Right? I think so. I think we're good. Are there any other conditions we can check? Things, yeah. So, okay, penguin operator. See. There's something very important, I think, is the fact that when we have a leftover block, and actually this is extremely relevant. Oh my god, is this something we haven't been doing? Oh shoot. Yeah, I think that, okay, let's go to every instance where we do a partition of worth it. So we need to check not only that this thing gets freed, but also that it gets coalesced with the things on its left and its right. So we're going to assert, first of all, that this is a valid block, right? Is valid block whatever the leftover guy is. Not only that, but by the end of it, that the previous block, right, of the leftover block is either equal to a no heap pointer or is not free at all. Not BK is free. Idrisi Irosh. I'm not sure how to pronounce your name, I'm so sorry. But thank you very much for following. Let's go. So we either do that or we also check this, right? We check the previous block is not free of the leftover block. And we also need to assert the exact same thing, but for, you know, for the right. So next. Perfect. Okay. Awesome. So these lines are going to be coming very handy because they're going to be present in basically every single occurrence of partition equality. So that's the first, first one, second one. So in this one, we also need to check, is this a valid block? Leftover block. And have you done your homework and merged with your bodies? Then the same over here, we're going to say assert that that is a valid block and have you merged with your bodies. And finally, here we do, is it a leftover block? So if it's a leftover block, assert that it is a valid block, whatever's left over. And also make sure that it has merged with the rest. Same here. Assert that it's a valid block. I know it's becoming a little boring, but it's very crucial we do it. Perfect. And then we're going to do it also here. So is it a valid block? All right, so the leftover block. I think we're going to have to solve a bunch of bugs related to the leftover blocks because we haven't been careful with them. Like we just simply free them and just don't care about what happens next. So these asserts hopefully will be able to catch all of that. And indeed, I think the best type of testing we can do is the asserts. Because the asserts can test for coalescing and stuff because they're part of the implementation. So assert that you have coalesced with your friends. What else can we assert? So I think these are the, let me see, git add. Git test for alloc. And then say added assertions for reality and leftover blocks after partition if worth it. So these are going to be a general test. Can we push this? Okay. I think that's the final code after adding all of the assertions, right? So previously it was 404 lines, now it's 538. But it's great. It's good that we've been doing that. So 1/5 became assertions. Do we need to check for anything else? So, add a bunch of asserts also to arbitrary. Right, so we'll debate whether or not we want those asserts in the red black tree. I think we do. But for now, let's try and see what happens if we run the previous files for which we have not much information, but we do. Where is it? I don't know why I'm looking for it. Let's just do make test. So we made test. Okay. It's time to test the truth. Will we get an assertion error? And my guess is gonna be yes. Oh shoot, we got a seg fault, which is even worse. So something that we did with the asserts introduced a seg fault. No. Okay. Yeah, this is not fun. Literally, there is a reason why it's called SharifSegfaults. It is because this is the most common error that I make, and it didn't like one of the most common errors when it comes to C and C++. So it's a hard life out here. It's a hard life. Happy Leto Clock. That's the best name I've had. Thank you for following. Thank you. So let's see where the segfault happens. Let's just run it and wait for the debugger to catch some segfault. Hello, debugger. Why are you paused? Okay, continue. Oh, is it trapped in an infinite cycle? I think it is. Yes, it's trapped in an infinite cycle. What's happening? Wait, this wasn't happening before. Why is it trapped in an infinite cycle, bro? Huh? What branch are we in? We're on main, right? Yeah. Yeah, 1 second delay steps. Yeah. What's going on? Okay, so I want to take a look at the git log. I want to know if it's something we introduced or was there before, because previously we had an error where I think it was realloc, where something was not being set to free, and we corrected that, but maybe while I was showing it out, I deleted it to show the behavior, and then it ended up staying. We realloc. Yes. Over here. No, it's there. It's there. Yeah, it's still there. Okay, now we need to figure out what the hell is going on and why this thing is not working. Am I executing the right file? Because make file, yeah, it puts it in bins, right? So make test. Maybe we can do make clean. Yep. And then, oh shoot, no. I think it's more like rmrf bins slash test and bins slash arbitrary test. Okay, so where is the error? Where is the error? DiePie says, bro, try ChatGPT. No. Let's make the test. So first, I want to run the test of the red black tree. And the reason for that is because the infinite cycle was inside of one of the red black tree functions. I think the red black tree is fine. Legend. Bro. I think the red black tree is fine, right? Yes. So we have success on that one. And that one's automatic, so we don't really have to check it. Then we run bins slash test. Yeah, we still have the infinite cycle. So guys, this is gonna be once again a very painful debugging session, but we're going to see where it happens. So let's see. Let's try and there you go. So let's run. And then we face the infinite cycle. So let's pause it. And now let's take a look at the call stack. So we get it to max node, remove, free, and it happens in test free too, in this guy. I swear I had the same bug yesterday. I remember I fixed it in the night. Oh yeah, it should. It's just that I think I haven't set the. Yeah, I'm dumb. Because remember how in the header file we did like, I think it was like define hashtag if def debug, right? But we never defined it. How do I define debug? Do I just do like? Do I just include hashtag define debug? And that's it. Yeah. Okay, perfect. So I think if we now compile that. Whoa. What? Wait, make test? Bruh, adding that just like, oh, I guess because everything is being compiled. Yeah, sure. So let's fix that. So line 109. 109. It says, oh, nothing was passed. Of course. And so block has been occupied and it will be the block. Right? This is fine. Yeah, this is correct. No? Okay. That's line 109. Then line 172, we also have an error with the printer and whatnot. For specifies type int, but the argument has type size t. Oh, so we just have to change it to u, right? Mainly free block size of lu, it says here. So hopefully it works. And then line 281. 281. 281. 281, 281. There you go. So I imagine this is the same. Should be a U or something like that. Oh, ZU. ZU. Okay. For and specifies type int, so it's the same error over and over. And I think we just need to do the ZU all over and over again. ZU, ZU. Line 404, not found. Yay. We do this thing. We perform ZU and ZU. Right. Is it correct? No. Okay, so is it LU? Which one of the two is it? 404 LU. Is that okay? So it seems like it doesn't complain with this D, but it complains with the zoo. So let's just do that. Line 534. 534. We have this other problem. where it says, okay, so I imagine it's like LU. And that's it. All of the warnings should be gone by now. I think the extension is just low. That's why it's still showing mistakes, maybe. Brother. Okay. So do I just put D for digit? And then here, the size is still complaining. This is probably zoo. Perfect. Oh, I see. Perfect. It compiles. I think it's better to do what you just suggested. What you just suggested, instead of this, we should do the what Rudifant was suggesting, which is in the flags of the make file include ddebug. Reset. Then we make that perfect. So let's run it and run test. Oh, sorry. It's /bins/ test. Segmentation fault. What? So when we run it in the console, it just segfaults. But when we run it in the debugger, it loops. What? What? Okay, time to investigate, I suppose. Let's see what it is. Cantai no llores. Okay. We enter test 32, which is the place where the bug is happening. I want to take a look at memory too. We say, yeah. I assume so, but like, I don't think we have instances of recursion unless the asserts are in a place where they like generate some sort of recursion, which could definitely be a case. But the loop is not even recursion; it's a while loop. So that's what has me a little confused. 5D60. Yeah. And then the display name is just, I'm just gonna change it to heap. Yeah, that's why it's strange, right? Because it's like, it's not supposed to happen. Like, what are we doing? Okay. Let's see, we initialize, we now look, and it seems like all of the asserts perform well. This is the place where everything fails. So P3 is this guy. Right? This guy starts here. So let's see what happens inside of MM3. We enter, and then we should see the log of freeing block or something like that. Freeing block. Hello? Where is my log? Why is it not printing anything? It's okay. Then we assert that it's a valid block, which it is. We assert that it's not free, which it is. Then we set its size to be whatever the size is. And so now we should see the header, the footer changing, but the footer is already to 38, so there should be no problem. Then we set it to be free. And so now this 39 should change to, well, it doesn't change, right? The thing that should change should be, this guy should change to a 12. Yes, okay. So we have still the 39, right? We go to the next block, we go to the previous block, and it says there is no next nor previous block. And that's a huge problem, because there's clearly a previous block, right? This block over here is one, and this block over here is the other one, right? Because if we go to MM test, we have P1, P2, P3. So P1 and P2 exist, and we're only free in P3, so P2 is still a thing. Why is it just deciding to ignore... What? Well, so this is the error. I see. So what's going on when we calculate the previous block? Why is it not getting the right thing? Let's take a look at that. I wish the debuggers could go back in time. It would be so great. I know side effects are the reason we cannot do that, but it would be great. Okay, we get to the previous block, right? So the previous block of block... Hello? Why are we freeing block 24? What? Oh yeah, that's fine. Okay, wait. Let me add a breakpoint here so that we know that we're starting the test. Yeah, sorry about that. Let's run it again. You also removed some code where you didn't know why it was there. Maybe it fixes a crash. If it does, it would be really bad because that code, we were looking at it and we were like, this makes absolutely no sense. And I think it was a typo because we wanted to write n block instead of block. But maybe that's the reason. I just want to investigate and see that it's actually that. So we can skip this, we can skip this, we can skip this, we can skip this. There we go. Test free 2. We enter this. We allocate, we allocate, we allocate. We free, we write, we write, we write, we write. And now we free. And so here we go and say, yes, all of this is correct. Set the size, set it to be free. And now I want to take a look at the memory inspector. So now you, my guy, are getting edited to be 659 to 100 659 D60. Perfect. And so now we take a look at the previous block, and what ends up happening is, let's go. So this shouldn't have an X block, which is correct. P3 doesn't have an X block. Now if we enter this, we say, well, if your next block is the red-black tree. Oh, if you are the first block, right? So if you are the block that's equivalent to the next block of the ghost node, then return null pointer. We should skip this. Yes. So now what kind of black magic are we performing? Right now we're at 39, right? And so what we do is... Oh, I remember changing the order of these things. Oh no. Okay, I remember when I changed the order of that and I was like, oh wait, we already had a function for it. And then it like actually was completely incorrect. There's a reason why. So this was not the code I modified. I like deleted. This is something else. This is here. So what happens if the block previous to us is not allocated? Sorry, is allocated. If it is allocated, it is allowed to override the footer with whatever information it prefers. So when previous block goes and checks, it checks information that's completely bogus, that is like user information. And so now it interprets this as the size of the block and thus goes like super far away. And for that reason is that we get a p block that it's like a huge number because it like underflows. So it subtracts this huge number, given huge in the sense that like, you know, right? It subtracts this huge number and then it overflows back. And that's why we see like 4 billion something. We can only calculate the previous block, and that's why it was this way. We can only calculate it to be over here, which is what I had before, right? I had it here. There was just no warning telling me that this was gonna happen, which I guess there shouldn't be, right? So we first check, well, is the previous block free? Is prev free for this block? If so, then it is safe to access that information, but only then, right? I think it's bk prev free. Let's wait. Let's wait. Let's wait. Oh, I see a message in chat. Give me 1 second. We're trying to I want to not lose the thread of what we're doing because block previous free. So I think it's also very important to note. Important. Do not do not access or like do not use prev block unless you know that the previous block is free. That is a great assert to have. So whenever you're accessing prev block, assert that the block you're talking about is a block that's not free. Sorry, a block that is free. So BK is prev free. BK prev free is true. And I need a clarifying comment here that says, if allocated, user data could have overridden the footer, right? Guys, give me a second. Give me a second. I promise I will read your messages. Right now, if allocated user data could have overwritten the footer, thus, we can only do this if the previous block is free, and thus metadata has been re-established. Re-established? Is this how you write it? Re-established? Or re-established? Great question for Firefox. Let's see. Oh shoot, no. 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 Oh no. Oh no, guys, we sorry, I tried to open Firefox and then everything went rogue. I guess I'll ask you guys, is this how you write it? Reestablished? I'll also try to look it up on my phone. Let's see. So with double E, ooh, that is an interesting feat of the English language. Sure. Okay, and thus metadata has been reestablished. Thank you, Rudinfant, and thank you, 3M Cried. Okay, let me read what your messages say. Okay, so you also removed some code where you didn't know. Oh, okay, yeah, and we determined that this was not the thing that was moved. Hi, bro. What would you suggest to a newbie coming to coding industry? I'm thinking about front end and shit like this. I just really don't understand how to start with an actual learning and how to add coding to my daily basis. Okay. I guess one question I would have is like, what experience do you have? Is this your first time coding ever? Or have you done maybe things in the past? Maybe you've done like a little game or you've coded a little program. What things have you done in the past? You know, where are you in this journey? To simplify the question. Coding Lara, are you actively learning and reading or you already know how to make it? Wait, Coding Lara, do you mean like are you responding to 3M Cried's comment? Or are you asking me? I'm not sure. But yeah. Polygon, thank you for following. Yo. And same for DiePie. So I was asking you. Oh, okay. Wait, when you mean actively learning and reading or you already know, it's like for the memory allocator? Or for the debugging session? For the debugging session, no, I don't know where the bugs are. Well, I guess that was stupid of me to assume we were talking about the debugging session. Uh, if you're talking about the memory allocator, yeah. So what I did was I said to myself, okay, let's do a memory allocator. Right? I want to know how it works. Let's create one from scratch. And I just went. I had to go on the cult train to visit a friend because we're going to a national park. And I just pulled up my laptop, decided in that moment that I wanted to code a memory allocator, and then looked up on YouTube the Carnegie Mellon University lectures for memory allocation, which are only 2 lectures. And they sort of say what a memory allocator does, what external fragmentation is, what internal fragmentation is. So they define all the basics, and then they show like a very basic memory allocator, right? Which is an implicit lists memory allocator. So it only has the size of the front and the size of the back, and nothing else, right? So I was like, okay, that makes sense. That's how a memory allocator works. So great. Um, like I need, I knew the spec of the memory allocator after those lectures because they defined all the concepts and stuff. And after that, I just didn't look at anything else. You know, just just like try and code the memory allocator from scratch and like come up with that design from scratch, taking no sort of external inspiration from something else or something similar. Just because I also consider the part of the design very important and like, considering all of this stuff. So yeah, that is the methodology we've been following. Um, but yeah, Penguin Operator's back. Let's go. Everybody say hi to Penguin Operator. Um, Emma cried, you're saying, I have experience. I've coded a little HTML, CSS in 14 years old trying to make websites for a living back then. I coded with C Sharp. Also, I created a game with a YouTube guide. Now I'm 19 and I thought that it would make sense to try something again. Maybe I like and enjoy it more. Thank you in advance, by the way. I appreciate it. Pengu! Let's go. If someone's kidnapping you, blink 2 times, Sharif. Brother, what do you mean? I don't. Wait, what? Why do you say that? Anyways, I'm assuming you have gone to uni and currently work in low-level positions. No, I'm a student in college. I'm a student in college yet, still. So welcome to the chat, L7 Mon. Maybe chat one's on Lemon, not sure. Um, ooh, whoa. H8 D13. So Haked D13. Haked die. Sure. Hello. Ever looked into NixOS Nixstore codebase? For Atomic FS principles, it's quite interesting. No, never really looked into it. Um, I imagine FS. You mean like file system? Let me know if it's something different from file system. But I know like the basics of a file system. Inodes and stuff. Not much about that. Good luck then. Hopefully the job market is better by the time you graduate. Yeah, hopefully. But I haven't forgotten about your comment, Mkide. So, I mean, people in the chat can also chip in on what you guys think about Mkide's position and what they're saying. I'll read the message again, right? Mkide is looking for... Temporary, you're saying, hi bro, well, what would you suggest to a newbie coming to coding industry? I'm thinking about front end and shit like this. I just really don't understand how to start with an actual learning and how to add coding to my daily basis. Then he says, well, I have some experience with coding. I've coded like a little HTML, CSS when you were 14 years old trying to make websites for a living back then. And you also coded C# and created a game with a YouTube guide. Now you're 19, and I thought that it would make sense to try something again. Maybe I'll like and enjoy it more. Thank you in advance, by the way, and I appreciate it. So yeah, anyone can chip in if you want. I'll give you my opinion. So currently, I think there is, and I feel it's like a very common advice, but I feel it is useful. The best way to learn is through projects. Like, do you know, like, don't rather like, many people are like, oh, look at YouTube tutorials. I personally think that's maybe not the best way. What I would suggest is find a project, find something that you're like, all right, I want to do this, and then start working on, you know, the that specific project. If possible, embark on a project that you don't necessarily know how it is going to work or like how to do it, right? Because if you throw yourself into the void without knowing what's going to happen, right? You do know that eventually you'll have to get out, right? There's like, just throw yourself into the void because you know that eventually you have to get out somehow. How? I don't know. But there is a way. So if you just do this, right, it's going to be better. If you, it really depends, right, on what area you want to focus on. Maybe each area has like specific things that are helpful, but it applies to all of them that a project would be good. The shape of that project depends on the area. If you're talking about front end, um, I'm not sure, I'm not very familiar with front end. So I think if somebody that's more experienced with front end in the chat can maybe contribute some sort of answer, that'd be great. I think things like, I don't know, do you have a personal portfolio? Right? Do you have like a website for yourself? Something that's, if you want to apply to a job or something like that, your personal portfolio is, if anything, something that you're very motivated to do because you'd better be good, right? It better be like, the website of mcry.com or whatever your name is.com could be a good one, right? It's very basic. It's something many people have done, but that doesn't matter as long as it's something that you care about and that allows you to push through. So personal portfolio would be great because then it's like, it's for you. The motivation is there because like, it's for you. That's what other people are going to see when they look up your name, and you're going to be deciding it. I think, and there's many possibilities to what you can do with it. So, there's like people like are crazy and they do like 3D stuff with Tree.js, right? So let your imagination fly on that front. It's like the only front-end project that I can think of immediately. It's a very basic one, but it's a good one. Other than that, I think you can just look up online front-end projects. I'll give you another example. Dijkstra's algorithm, right? So if you create a user interface that allows people to have a grid of blocks, right? Click points in that grid to mark as destinations, so point A and point B, and then, I don't know, put obstacles in between, and then be able to generate a graphical, visual of Dijkstra's algorithm solving this maze would be great. It's like a project where you apply algorithms, where you need to apply the user interface, where you need to apply a bunch of stuff. That could be another project. Let's see. So, Lemon, you say in MCRI, do you have specific industries or job positions you're interested in, or is it more of a personal project? Good question on Lemon's side. I got 11,000 comments in the last 360 days. Do you think I'm losing my mind? Maybe. Maybe. I think it's more of something personal. I just want to obtain some good skills in code for myself. And then, of course, I'm looking to apply for a job, but I'm not sure which job position. I'm interested into front-end UX UI, I think. I got a portfolio, but I work on it. Thank you so much, guys. Yeah, I think there is also another sense where you should also try to be very curious about things, and like, rather than becoming someone that just does front end, because there's a difference between me knowing React, right? I know React. So what is the difference between, say, me and you, right? Or between me and an actual front-end engineer? Well, the front-end engineer, although we both know React, they have the power of decision-making when it comes to front-end. They have not only the experience, but also the knowledge necessary to create a good UI. So rather than sort of focusing on learning new technologies, which is something you should do, but you shouldn't dedicate like 100% of your time for that, maybe 30% of it, and dedicate the rest to perhaps learning the theory that is actually important to it. What makes a good UI? You know, rule of three, how to design an actually good hero, how to, etc., 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 right? Theory of color, and so on, because that's gonna be the thing that makes the difference. In the new world, of course, for example, right, if we are to mention once again that everything comes back to AI, Sharif, why do you keep talking about AI? I know, guys. I know. But, you know, it's like in the end, AI can also write the code, right? So you need to learn about the code, but it's also very important that you train your decision making when it comes to the things that you're doing. Don't do things with AI. It is a bit like you know, like if you're doing a personal project, just don't use AI. Why? Because although AI can write the code, the way you train your decision making is by practicing and going through the struggle of writing things yourself, because only then will you understand why things are the way they are. So I guess I feel it's a very basic advice. I'm not saying anything new, and it's in fact something that you would say like right, kind of dumb. Like don't use AI, use personal projects, and make sure that you train your decision making rather than just writing the code. So yeah, I hope that helps. It's my opinion, right? Like people in the chat can also contribute and say like, no, actually, I think you're wrong. Like, well, actually, I didn't mean to mock, but I make voices from time to time. I like, actually, no, you're wrong. Like, it doesn't really work this way. The front end industry is a little bit different. Feel free to anybody in the chat. Infinite Coder 01, I haven't seen you in a while. Welcome back, bro. Where is the practice in your equation? Yeah, I think I put it there. Thank you so much for genuinely appreciating your call. Thank you so much. A while? I mean, were you here yesterday? I was just GMTKing. Interesting. In other words, bro descended to hell. Came back just to watch the stream. Anyway, then to whoever has to deal with GMTK, I wish you luck. Oh, Teye Ui1. Thank you for following, and same for Jenktron. Yo. And John Black GG. That's an interesting name. Yeah. So, and that is little less weight on my shoulders. So I want to be like sure. Is infinite coder. So GMTK refers to like the I don't know much about it. Is it the game jam that was taking place? It was like something, if I remember correctly, game maker toolkit, something like that. Or is it something else? Yeah, okay. You say low level stuff in your bio. Did it ever make you want to get into OSS Linux stuff? I feel like I may be interested in it, right? For now, it seems like low level things really call my attention. Once again, I'm still in college, so I don't have a professional job still on some sort of position. And so it's like I feel like I would be interested in it. I would be interested in it. I haven't done anything like contributed to it. I've done like projects on my own, like a memory allocator. I've done a thread library, a virtual memory pager. I've done a network file system, all of them from scratch. So like it seems like I like it, but I maybe the Linux world is like a little bit more different than that, because of course all of those things have already been created. But really, GMTK is Game Maker's Toolkit, which is a YouTube channel who runs the most popular game jam in the planet. I see. Oh, pretty good. Um, as much as I hate to say it, in my opinion, it's better to keep personal projects and careers separate. And I mean that as in looking at what the job market is actually looking for. From my view, front-end positions are more at risk and somewhat saturated, whereas stuff like low-level programming, machine learning, and so on are more desired. If you really desire a career in front-end, then don't let me hold you back. Do what you think is best for you. I think that is a great message. I think you should also listen to Lemon's position. Um, I don't have much experience on how the front-end industry is looking. I do see that it is at risk, as Lemon is saying, but I feel this is more of a whatever I tell you, don't listen to me. Listen to maybe Lemon that may have more experience. Um, because of course, right? I'm not in the front end world, so all the time I hear front end engineers are done for, right? The AI is replacing the front end engineers, which is equivalent to how the normal peoples here, software engineers, are going to be completely displaced by AI, which is not really true, right? So I'm not sure if that's happening with frontend. It seems like it is. So have that in mind. I feel like what Lemon is saying is valuable. I have ported the Linux kernel recently. Has been an interesting experience. Brother, why are you infinite masochist wine? Open source is nice for that. Just find bugs and fix them periodically. Yo, that's pretty good. I just saw your video on YouTube when you were 15 years old. Have you continued studying that way until today? Ooh, so did you discover my other channel? Uh, yeah, that's interesting. You ask if I'm from Mexico. No, I'm originally from Colombia, South America. I came here to the US to study, so I've lived my entire life in Colombia, and came here to study to the US. So yeah, and have I continued studying that way until today? It has changed a little bit. I have focused more on coding and math, which are my majors. Right, I'm studying pure math and computer science. So university takes a lot of my time. But yeah, I've tried to stay as disciplined. I think, sometimes you struggle with motivation and stuff, but yeah, hopefully we're on the right path. Um, Ain't no way our low-level job marketing isn't. I don't see much of a future for OS creators with AI being a thing. You know, it really depends. I would say there is definitely a future. I do have to admit, I don't know what the future holds. But OS developers and this low-level stuff, I feel like they require a lot of attention to detail. And I feel like more than that, and it doesn't only apply to this, it applies to any sort of system, right? It's not only OSs, it's basically every field of programming. A good design, a good interface, good systems principles are something that are seen from a landscape view, from an overarching view. And I think it's that decision making that's going to become important. So I don't think AI is something I'm really scared of, something like that. There's just as much value in digging docs, testing stuff, etc., than there is in coding it, to be fair. Yeah, that's completely true. Yes, I'm just trying to get into coding overall. I'm not really sure with what I should start then. That's really hard to understand what I should pick up. I feel so lost. I see. So, MCard, I think it really depends, and that's why we're mentioning you should enter programming from the side that you find attractive, because what matters when you're starting, rather than let me make sure that I'm looking at the right things, is keeping up with the motivation. So it's a combination of both, like what Lemon was saying, but make sure that what you're going to do is something you like, rather than being completely what the industry says. Do a mix. It's something that you like and something that is relatively relevant to the current industry. For coding overall, and if you really want to learn, algorithms and data structures are always important. The lead code stuff is important, but that is maybe not as interesting, right? So maybe do it on the side and stuff, and projects, personal projects are the thing I would definitely suggest. Gogo04, I already have my AI making OS components from scratch in a loop, improving it over time. So, I mean, I feel like OS may be not the right thing to use it as an example of like, how AI can replace it, because most of the OS stuff is out in the internet, right? It's very simple for me to just go to the Linux repo and see how it was implemented. So of course, like AI was trained on all of this data. If you ask it to implement a virtual memory pager, there's going to be thousands of implementations from thousands of people, probably in universities and stuff, that it's able to copy, right? Or not only to copy, but to be trained on. So yeah, in this case of an OS, for the components that already exist, yeah, I would agree with you. It would be easy for an AI to implement. But I feel that is a little different from what it means to be an OS developer, right? Without being an OS developer, without knowing about the field that much, there is a difference between creating what already exists, which is not a special skill, really, or well, maybe a special skill if you really do it from scratch and like try to, you know, but anyone can create what already exists just by sort of looking at the code. The thing is the experience you need when it comes to creating something new, or rather than something new, adapting things to specific needs, right? Um, so yeah, don't worry too much about it. Mostly look around to see what you like the most, but be mindful. What Lemon is saying is exactly what it is exactly that, right? Building AI design will be the new thing. Yeah, that could perfectly be the new thing. Completely agree. Go full. I just don't know how to start overall. I've surrounded myself with games and cheap dopamine for over 4 or 5 years already, but now I understand that I should get my life together. It's so hard to find and comprehend with like, yeah. But I really appreciate all the response. Yeah, it is. I understand it's something very difficult. It like only you know what you like, right? Um, game development could be another thing. Although there is a difference between liking playing games and developing games. Like people think like, oh, you like games, you would enjoy game development. Um, maybe you do. Right? So just find something that interests you and do. And yeah, that's the. Yeah, yeah, yeah. I find it quite funny that everyone was like, "Oh my god, my kid loves to play games. He would be a great game developer." Like there is a huge difference in the two, but often they overlap. But sometimes, making games is way harder. I tried, but it is that struggle that would be great for you for you and for your purpose. Um, Even like following the tutorials, right? Just follow tutorials, but make sure that you're coding on your own rather than just watching the tutorial. 324B2L or I. I don't know if that's an L or an I. Welcome to the stream and thank you for following. But yeah. Oh, all right, people. Yes, thank you for following you. Y'all are cool. I appreciate the vibe. Yo, let's go. Perfect. So, people. I was a little aside. It was a little break. But remember, never give up. Never what? We never give up. We focus. We continue. It is the mindset, the grind mindset. We need to grind. We need to be constantly oh my god. Dude, I sound like some like some like brainwashed YC kid right now. Yeah. No. We should continue with the memory allocator for a while. To be fair, some games, for example, Minecraft, may hint at the person possibly enjoying game development. Yeah, that is completely true. So sometimes they overlap, some other times they don't. Yeah. What language you're coding on? This is C. C. Just the letter C. Yeah. But yeah. All right. So, guys, what were we doing? Oh yeah, we were doing this assert. We were asserting that the previous world was free. And yeah, I think that assert solves our issues and everything should be working now. So what happens when we compile and then we just run it? Oh shoot, wait! Oh no. Okay, line 135. Hello. Yeah, it failed here. Oh wait, it's logging! It's logging! It's logging! Allocating 24 bytes. Whoa, wait. It's logging. Let's go. I think I forgot, unfortunately, to print new lines. And so now everything is squished. Um, do you guys know how can I make it automatically print like new lines? Cause like I mean I guess we'll just have to add this all the time. Sure, 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 sure. Um, new line, new line, new line. Oh yeah. Me when I forget new line, you can always screen. Yeah. 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 Unfortunate. I can always create a print function. I guess so, but I'm halfway through the editing of the debug print line, so I think we're gonna just continue this way. I should have done that, but now it's a sunk cost fallacy. Um, me when. Anyways, yeah. Um, slash n slash n slash n then slash n. Yay! Sunshine and rainbows. When did you start programming? I started when I was very little. I was like 9 or 10 years old. I started with Scratch, uh, like Scratch, the little programming language, the cat. I started with that, and it was very interesting. I was happy. I think like I still have the games that I made back then on Scratch. Um, that's a great idea. Maybe we could take a detour and take a look at those games. I completely forgot about that. But yeah, I started with Scratch. Then I started with Python, and I was very obsessed with the idea of creating a virtual assistant like Jarvis for Iron Man. And so I created this assistant. I think its name was Abner, Abner. It, for no reason. I just looked up names and I saw that one, and I was like, oh, right. Um, and of course, like AI didn't exist back then, and you cannot ask a 10-year-old, 11-year-old to code like an AI, a conversational AI. So it's just a file full of ifs. If the first word is video, play the video, right? Like if the first word is music, then grab the next three words and look that up on YouTube and so on. It was very fun, and I lasted like 3 years trying to. First, it was Abner. Then I created another one that was called what was the name? Some, Somay, Some. And then after that, I created a different one that was called Karen from the Spider-Man movies, from Spider-Man Homecoming. Um, and I connected it to like an Arduino, and then I learned Arduino to try and turn on and off lights. It was never a useful thing, right? Because like to use it, you had to know what the structure was. You had to know how the ifs were programmed. And so I could use it and do all the stuff, but just because I was the one who coded it, and it wasn't really advanced at all. And yeah, and then after that, I went to school, and as I think I mentioned this yesterday, I was married to Python, completely married to Python. It was like the love of my life, Python. But during school, our programming instructor, he gave us an assignment to code a bingo with a little interface because he wanted to teach us Qt for Python, which is absolutely, crimes against humanity, is trying to teach user interface in Python. Um, but he did that, and then there was this classmate that the day where we had to submit the assignment, the professor called me to the front because he was like, "Oh, your bingo was pretty good in Python, right?" And it was as good as a Qt interface can look, which is pretty bad. Um, so I showed it around, and I was very proud. And then this other classmate, he brought his bingo, and he didn't code it in Python, right? Because the professor never said to code it in Python. I just coded in Python because I liked it. He coded in JavaScript and in HTML and CSS, and that thing looked so beautiful. And that day, everyone was amazed at his bingo. And so I took it personally. so, and, so, and so in 1 week, I went and learned HTML, CSS, I learned React, and I learned Node.js just so that that would never happen again. And so I dedicated to the web for like, what, 2 years after that? Because that was like junior year of high school. I dedicated to the web and I did like web stuff and web projects and like little websites and stuff like that. And yeah, by the end of high school, I started getting interested in pure math, pure mathematics. And then I came here. Here is where I got introduced to CSS, not CSS, to C++, um, a little bit more. And then I started realizing that what I liked was understanding how everything works, which is part of the reason why I liked pure math. And so that's how I was like, oh, okay, I'm interested in programming, but I want to, more about it, and so on and so on. Then I had a class in university about operating systems, and then that absolutely changed me. And here we are. Yeah. Um. And yeah. What about new lines? Yeah. Thank you, QXZ. What is the new makefile user doing? What do you mean the new makefile user? Do you mean this guy? It's just compiling a program. Yeah. Can't you just add into the function? Yeah. What would you name a function like that? Debug printf. Yeah. I had my first computer when I was like 17, and the moment I got it, I installed Linux on it because Windows was version second gen processors. Then I just fell in love with operating systems. Wait, that's a pretty good story. Yo. No. All programmers united by our collective hate of Windows. Anyway, well, like Windows, I use Windows for like basically all of my life. I changed to Linux only like extremely recently in my desktop computer. But yeah, so I'm yet to live that transition. Um if you started from scratch, you must be young. I'm 20. I'm 20 years old. I want to write Docker clone in C. No, thank you. Actually, like that might actually be like a good idea. I'm not sure how interested I would be in it, so probably I wouldn't do it. But it is like if I really like Docker and everything, that would be the next project in the channel. But yeah. Anyways, let's try and run this thing. Bins/mm_test. Blah. Assertion failed. So we did something wrong. We did something wrong. Where is the wrongness? The wrongness is in your heart. Okay. Malloc. So let me just do like a little like printf and then starting malloc test dot dot dot. And then here we end it. And never forget the new line. Then here we end it. Let me say dot 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 finished malloc test. Great, and then we do the same for the rest. We just write starting 3.1 test, and then we also copy this guy. Okay, there you go. Finished 3.1 test. Great. Now we go to the top, then we copy this, and we put it here. Starting the 3.2. Actually, I think there is a better approach to this. Copy this and paste it here. 3.2. And then we paste it here. We say starting the realloc1 test. This is the boring part. And then we do finished realloc test, realloc1. And here it's we starting realloc2, and then finishing realloc2. Where is it? There you go. Yay. Then realloc2, and the final one, which is realloc shrink. Starting realloc shrink. Or shoot, no. Okay. Starting realloc shrink test, and then dot dot dot. In the end, finished realloc shrink test. Yo, perfect. All right, we did it. Let me read the chat. Seconds. Monterey Docker Clonia. Are you familiar in graphics? No, not at all. Absolutely no idea. Making a container would be cool, although I don't know what a container is, just theory. But what it does to memory? Yeah, I have absolutely no idea how it works under the hood. I'm actually re-practicing stuff to teach myself how to make a web server. Yo, let's go, Codebara. Web server in C or writing core utils from scratch. Hey, that's pretty good. That's an excellent project. Yay. Yeah. But yeah. Anyways, graphics would be easier if it didn't have so much math. I guess that's the usefulness of math. You know, that's why you gotta learn math. Math is pretty good. I don't feel like I like math a lot, but okay. So we're starting the free one test, and we're failing an assertion on that test. So let's see what the call stack tells us about the assertion. Ain't no mountain high enough. Okay. Campivara, thank you for following. And Ese Zeta, thank you for following too. Yo. All right, let's continue. We go here. And I think if I do this, then we're going to enter the... Oh, what? Oh, yeah. We continue, we continue, we continue, we continue. We assert, we assert, we assert. Ooh. Problem. Oh, of course, of course, of course, of course. So we have a problem. We have a problem in our asserts. So it's possible that the pref block just like doesn't exist, right? Like it's not that it doesn't exist, but like the previous block is not free, and thus we shouldn't be, you know, using this. Give me 1 second. I'll be back. Hello. Okay, let's see. How do you host your website? Do you pay for that, or just curious? Okay, I see. Code and Barra, I don't. I am in school too, and GitHub gives domain for free, and it's hosted on Vercel. Yo, glad to know that you're in school. Yeah. Oh, okay, makes sense. Perfect. All right, people. All right. We gotta we gotta find a way in which to kill the problems with pref block. So when we need to access the previous block, it is likely that, you know, um I feel like there is no need to access this, right? We would say not block. So it's important what the order is, right? So not block is bk prev 3. So either the previous 3 is no longer, so left, so what was it? I think we were looking at leftover, yeah. Either your thing on your side is not free, or you actually just don't have anyone, right? And so I think this is a better way to do this assertion. Let me find all the ways in which we use pref block. So we use it in a bunch of assertions, which we shouldn't be doing. Okay, here. So instead of that, it should be this. Leftover block. And here, yes, yes, yes. Okay, instead of that, it should be this. So then we put block. I'm sorry, no. No, 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 no. Oh my god. Where was I? Here I am. All right. Then I put block. Perfect. Then we take a look at pref block again. Prev block. There you go. And now we continue a search. Pref block, this one's fine. This one is not fine. Needs to be replaced by the thing. Doop, doop, doop. There you go. Pref block, we don't need that. We need this instead. So perfect. We continue here. Then we, assert and we do all this stuff. And here we do the exact same. Well, it's taking us a little while. It's fine. Let's see, now we jump here, pref block, that's the definition. This is fine, this is fine. This is fine. This is fine, this is fine, this is fine, this is fine. This is fine. Okay, perfect. I think we fixed it. We fixed all of the assertions. Make MM test, reset. Then let's see. Let's see. This thing is really complicated for a newbie like me. No, I mean, don't worry. You should hang out, and if you have any questions, let us know. Let me know, and I'll try to answer as sincerely as possible. Questions about the memory allocator, about what we're doing, how does it work. Coding bar, but I will be graduating in 3 months, so I wasted a lot of crucial learning with AI. That's never consistent, but I'm good at searching, is all I can put on my resume. I feel, no. Coding bar, brother, don't say that. You're interested in OSs, you got your, there's a lot of future ahead. Like, what? You know? Like, the fact that you're on the stream already says a lot. It's just pretty good. Because, not everyone clicks on a stream that says coding a memory allocator in scratch. Like, that takes a special kind of person, as I've said, from time to time. Even my website was generated by a static site generator Astro, which is like an engine to make own website with template. You just change the info. I see. Yeah, I've done my C advanced exam like the other week. This thing really seems a lot more complicated than what I've done. Well, you may have more knowledge of C than I do, because I just learned C for this project. Don't know many features of the language, but yeah, I think any questions you have, we're completely more than happy to answer. But yeah, let's make the test and then let's run it. Assertion failed. Ooh, we have another assertion failed. People, what is it gonna be now? If we run the debugger, it should tell us where the assertion happens. So it's not in free 2. It's not in realloc 1. It's not in realloc 2. Oh, it is in realloc 2. Never mind. What is the call stack? Ooh. Ooh, this is very interesting. So here we had an error. We had a bug. We had a bug. We had a bug because we shouldn't be accessing prev block without checking whether or not the previous one is actually free. And we use it quite often. You know, yeah, we use it over here for the second case because we need to look at a previous block. And so memory allocator is sort of tool for dynamic memory, I guess. Yeah, basically. It's the equivalent of malloc, right? Malloc, it's like memory allocator. So malloc is, we're just implementing malloc, free, and realloc from scratch. Exactly. So, okay. So how do we fix this? How do we make the user actually, sympathize with the fact that we don't. Okay, so how do we make it? So this is an important design decision, guys. So notice that we cannot access prev block if we don't know yet that the previous block is actually free because of the things that we've been mentioning. So that being said, right, how do we make that simpler, right? Because, it's good if we write the code like this, rather than having to say, eliminate this variable, and then once you have to do the check, perform the check over here. Right? It's like, I don't, it's like not that good. So one thing we could do, right, could be something like, previous block, and then just say something like this. So if the previous one to me is free, right, then I access prev block. Otherwise, I give you a null pointer. Now this could be a way, right? Because we say, oh, this thing is going to be a null pointer if I just cannot access the previous block. The problem is a little misleading, right? Because this technically, right, it's not the previous block. You could have a previous block, but this thing being a null heap pointer like signals to the programmer like, oh, there is no previous block. And so maybe we make a choice in the future where we say, oh, p block, if it's null pointer, it means that there's nothing previous to us, and thus we decide to act on it. And I don't want that to happen. So either we need to reform the code in some way or do something of sorts, right? Because the prev block is not really work. Oh wait, I've seen messages in the chat. So what are you trying to do? The title. Okay, that's kind of interesting. That's simple. Void malloc, update stream title, coding a memory allocator, socials return. No. Yeah, don't mind if I at the start of realloc, can there be a pre-prev block? Would it not be coalesced? Yes, there can be a previous free block. It is completely possible because that is in fact the situation we had with the 3 blocks that we always think of, where you have like, oh shoot, we've done a lot of stuff here. Let me erase all of this. Wait, let's zoom in and eliminate this one too, and this one, and this one, and the arrows and everything, and the size. And yeah, there can be a previous free. It wouldn't be merged with yourself. And the reason for that is we can have the scenario where, you know, I hate this menu. How can I make this go away? Brother. Okay, that's fine. Well, this one's allocated, this one's also allocated, and this one's allocated. These two get freed. And then if each of them is of size 40, and this guy asks to be changed to something of size 52, the only way we can do things is either expand them to the right, but if the right is small, like 10, then 40 plus 10 is 50, and thus we need to coalesce with the left. So there are definitely scenarios where the start of the alloc, where you have a free previous block, your current block is allocated, so no coalescing has happened, but you need to trigger the coalesce now, despite you being allocated. It's like one of the reasons why realloc was so painful. So yeah. So we definitely can have that situation, and that's what's messing everything up. So how could we do this? Because another way would be to just do what can we do? What can we do? But I don't understand why you can't access the previous block if it's not free. Oh, it's because of an optimization. That's a great question. It's because of our optimization. So when the way we design things is as follows. Blocks look like this, as you already know. They have size, left, right, parent, color, and extra and size. These three or these four fields, actually, why is this so thick? Okay. These four fields, right, they are used to keep track of things inside a red-black tree, right? We want to know whether or not, the left child, the right child, the parent, etc. The thing is, when we provide the block to the user, right, this thing is not being used at all because it's no longer the red-black tree. So this information doesn't really matter, right? It can be whatever. So what we do is, when the block is free, the header looks like this. When the block is allocated, we provide the user pointer to point here. So the user is allowed to modify all of this information, right? But then we realize, well, when do you need the footer? Well, you need the footer to coalesce two blocks, right? When you need to look at your previous to see if it's free, and then merge with it, right? That is the only case and the only reason why this is here, to facilitate coalescing. But if your block is allocated, you will never coalesce with it, right? And so what ends up happening is, well, do we really need the size when the block is allocated? Well, not really, right? And so we do this, right? We allow the user to write all of this information because it gives us even more bytes for the user to write down. And so now we decrease memory usage. And although these are 4 bytes, count that for every block that's going to exist, and it ends up being something worth saving. Now you may be saying, well, if I am a block, right, how am I able to know whether I can coalesce with the thing on my left? Because if I go to the thing on my left and all I see is user data could contain anything. So how do I know whether or not the block on my left is free, right? If all of its information is overwritten by user data. And so what we're doing is we are saying every block contains a field called prev3. And prev3 tells you whether or not the previous block is free. That's why we've been saying, like, oh, to know whether or not my block is free, I need to go to my next block and ask it, am I free, right? Because of this optimization. So if I save inside my header, inside the least significant, second to last least significant bit of size, the previous free, then I'm able to know whether or not I can coalesce with that previous block without even visiting it. So it is it is that situation, right? And so previous block, you can only know what the previous block is if this size footer is present, right? But when it's not, i.e. when it's allocated, then you cannot know. And so that's like the situation we're presenting here, where I'm like, we need to improve the interface because that fact is not being communicated at all. And like it's starting to, the code's starting to smell bad because of that. Like there has to be a better way in which we can convey previous block is not an actual thing that you can access. Like you need to make sure that that thing is free before you access a block, which the assert tells you, right? The assert tells you like, oh, right, this thing needs to be free. But while you're coding and like for the person that's reading the code, for it to be like evident, like, oh yeah, right, I cannot access this thing. Because many of our mistakes have been because of that. So yeah, I don't even know where I was. Where was I? Line 135. Oh wait, but that's the code stack, right? Um, block, block. Oh, I was right here. So could you do it like pref block if free? It is sort of what I'm thinking, right? Like that seems to be the only reasonable option, right? This is where building games comes in handy. Because you learn how to free memory, right? Yeah. Unfortunately, I don't have the games experience, so it kind of shows over here, but yeah. Could you do like pref block if free and then the block? So then the question is, what would that function return? Right. So suppose now that, you know, if the previous block is not free, then it maybe returns a null heap pointer, right? But then I'm not able to differentiate between two cases. The case where it's returning null heap pointer because the previous block is allocated, and the case where it's returning null heap pointer because I actually don't have a previous, i.e. I am the first block. Right? Like it's not really, what like evident. Also, why Rust is the best right now. Well, Rust also needs a memory allocator, right? So, uh, kind of not. Yeah, do you need to care about the difference? So my problem is usually notice that the way we tell whether or not something is the last block is we do something like this. We do next block. Yeah, there you go. Either you are the last block, so there's no need to coalesce, or this thing happens, right? So I think there are places in the code where, yeah, see, it's like either you are the first block, i.e., you don't have something to coalesce with, or the previous one is not free. So there are instances where we rely on this, meaning you are the first block. Are those instances significant enough that we should not implement the change? I'm not sure. But I'm pretty sure there are instances where we do this. Yeah, so you're always coalescing with three blocks. Yes. If the block on your left is free, right? If you're coalescing with the block on your left, yes, you're always coalescing with three blocks. Indeed. But well, I guess I see what you're coming and saying. It's like you would never need to access the previous block if not for coalescing. Right? I mean, you can always have two functions, right? Pref block, which always returns the block, and pref block if free if you need both. I mean, I guess, but now it's really confusing, right? Because then right, I would write prev block and then expect to get the previous block even though it's allocated. Question is, do you ever need a non-free prev block? Yeah, that's like the thing that determines it, and I think we don't. I think we don't because let me see. So prev block here, it's access fine, fine. So let's see what this prev block is doing. This one. If the previous is free, yeah, we're fine. Good, good. What is doing this? What is this p block doing? We are only using that pre-p block. P block when yeah, when we need it to be free. Block is free, so no instance of needing that. Right. Yeah, so we're fine. Then here we check that. Then here we check prev block. Okay, so there's no instance where we need a non-free previous block. Yeah. Okay, so previous block if free. I guess like the way you could potentially check whether or not you're the first is the way because prev block needs to return heap pointer if you're the first block. So there is a way in which prev block knows. And the way it knows is it checks the ghost node, if I remember correctly. Where is it? BK, prev block. Oh yeah, here. It's like, if you are the block that's after the ghost node, then you're the first. So I guess like if somebody really wants to access that, then they can just do this. Yeah, sure. Prev block is free. Sounds good to me. And so I'm gonna just have a sort of a brief returns the previous block if the block is free. Otherwise, returns no heap pointer. Right? And so now we just ouch. Okay, so now we need to say something like this, and then we can do, well, not only this situation, but also, or the previous one, so bk prev free of my block is just not there, right? Then I return no heap pointer. Perfect, and then we need to go to the header file and also change it. Yeah, prev block if free. And that should change things around, and then we should see thousands of errors. In 3, 2, 1. Oh, the C extension is just taking a little bit of a vacation. Previous block, let's see where we use it. So we use it here, that's fine. Okay, prev block. So prev block, if free, I assume. If free. I know I could just replace all of them. I just want to make sure that the behavior stays, that like each behavior that was expected is still there. Assert previous block if free. Right. Previous block, unless that. Okay, if the block is free. I think now we can change this to what it actually is, which is block is equal to prev block if free. We can simplify it a little. We say block, and then we can say, right, if p block is different from a no heap pointer, then we can access it, right? Perfect. And here, for this one, we do prev block if free. Let me make sure that this one's also correct. So here it changes. Here the behavior changes, right? Prev block if free. Prev block if free. Then we have a p block, right? And then this p block, this one's also a prev block if free. Okay, so we have p block, right? P block, and then this p block guy is going to go to here. Okay, p block 3. There you go. Perfect. So here we're using p block. How do we use it? We say it's different from a null pointer. It's free, and its size. Yeah. So it's still being used in the right way. And here we need to say prev block if free, and then prev block if free. And actually, now that I think about it, we can just save this check because like every single time, this guy, right? If your previous is not free, is also returned in null pointer. So I think we can just, delete all of these instances. Perfect. I think we're good. I see messages in the chat. Give me a second. I want to finish this and then I'll read it completely. Pref look if free. Perfect. Okay. Let me go here. We have question is, do you ever need a non-free pref look? Yeah. Sabi Dev, welcome to the chat. Yo, why the need for such a complicated allocator? I feel like linear allocators is really all you need. Well, we're trying to create an allocator that is the most convenient thing for a programmer, right? We're doing this for the sake of learning, so that's something that's worth noting. But we want to basically create malloc, right? And notice that malloc is not necessarily an arena allocator; it's just a general purpose allocator. That's what we want to do, right? So yeah, that's that. And Rudifan says, Sabi Dev, Arena cannot deallocate single allocations, which people sometimes want. Yeah, exactly. So we want to make it more convenient to use. And yeah, I think, guys, I think this is it. Is this it? I've said it like 30 times, like, oh no, yeah, we got it. And then fails again. And reset. Let's try and run it again. Oh, we failed even earlier. What? Oh, it's because I left the assertion. I left the assertion here, which I should have removed. Here, the previous block free, right? Yeah, this assertion shouldn't go there. So now we make this, we reset, and we run. Oh, yo, no assertion failures. Wait, that's incredible because it means like, in a way, right? Remember yesterday how I was complaining like, oh no, we don't have like a way to test whether or not they merge and like etc etc. Like the asserts do just that, right? Because if you check, oh my god, this is so good. Yo, let's go. Assert that prev block if free. Like the asserts do just that, right? Whenever you try to free something, assert that there's no free block to its right and no free block to its left. So that's basically asserting that like we are indeed merging the blocks. Because if you merge the blocks, it means that you whatever you have to your sides is already allocated. Because you weren't able to expand. And so this is the way to test the memory allocation. Yo, infinite glory, let's go. Yay! Okay. So now we should devote our time to just like create the most random applications ever, and be like, creating the situations as Ferrari was saying last time, where we do like, what if we have three blocks, and what if we free the two of the extreme, and what if we put this one back, and then we take this one out, and then we wait for them to merge, but then we actually trick it, and then we take them both off. Like we need to create those crazy situations to see if something like weird happens. But if we were somehow able to go through all of these things, like these programs that we had created, without an assertion failure, it gives us like a pretty good degree of confidence because like 1/5 or 1/6 of the code is asserts, right? Assert, 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 assert. So that is pretty good. I do believe in something. So I do believe it's better if we, you know, we need to beautify the code. I know. Right. Beautify the code. What do you mean, Sharif? I mean exactly just that. Like I personally, I like it when the code looks pretty. Personally, right? And like many other people too. Um, but personally, right? And like why, what is the ugly thing? Well, notice that like the asserts are mixed in with the rest of the code, and there's like comments everywhere. And, like, some there are some parts of the code that look good, some others that look like get away from me, right? So I feel like I would want to make it a goal to make it a little bit more beautiful and readable. Um, we're adding a bunch of asserts over here. I don't think we need to add asserts to the red leg tree. Like I think those are already there. We need to get rid of magical numbers. Let's see. I saw a message in chat. Rutified, yeah, Pokemon. Yo, we should be super happy. Well, that's because you wouldn't do that. Typically, how you use them is you have a scratcher temporary arena where you do your work and copy thing into a permanent area. Then you would nuke the scratch arena. If you need to manage resources, then you'd use a free list or pool on top of an arena. Yeah, exactly. Like, but that requires refactoring if you don't do it from the beginning. Yeah, it's a different pattern, but it's severe. Yeah, Sabi, like it is that like there are definitely, other ways to if you are a programmer, right? And say you're coding some sort of embedded system, of course, like it's gonna be better if you have your own allocator or a specific pattern. What we're doing right now is we're just trying to do the usual general purpose memory allocator, right? The one that a programmer would just want to say, please allocate this much and free this much, right? So we are the ones taking care of, the free lists and stuff like that. Yeah, that's the whole thing. So, anyways, great. It seems like it works. Which is, really happy about that. So I think we can just git add. We can just git add, and then that's gonna be our price to add everything to here. How could we label this? Do we label this like test? Do we label this test? Maybe refactor, right? Change prev block for. Yeah, no worries. Thanks for saying. Oh yeah, no, thank you, because it is true, right? Like maybe an arena allocator would be better for somebody that like it's more experienced. But yeah, let's see refactor. So we're gonna change prev block for prev block if free, and then prev block if free, fixed asserts, and then we're gonna include a message, and it's going to say changed. Well, title. Also, test runs with all assertions passing. Oh shoot, I need to amend. Git command amend, because I included some sort of slash and then a reset. Perfect. We're gonna git push. Yo, an arena allocator as next stream project would be interesting though. Maybe, but like, like, I feel we're a little tired of the memory allocator. We've been doing this for like 2 weeks, 3 weeks. I think I'm thinking of changing to something else. Maybe in the future though. But I think after the memory allocator, we're done. We're done. But yeah. Anyways, Anyways. So. What do we have here? Don't worry, take a break from allocators. Yeah, so now we need to get rid of magic numbers, which is the next thing you have to do. Um, by magic numbers, I mean, I think I remember seeing some of them where there was hex 62696760 I imagine that's your name in hex. Uh, I'd like to see what it is. Hello? Can we put that in the memory inspector? Would it allow us to? No, it won't. Oh, that's unfortunate. Anyways. Oh, cancel. Oh shoot, no. No. Okay. Can I just not look at it in the memory inspector? Come on, dude. The memory inspector. Okay. Anyways. Yeah, I hope we gotta see what your name is. So 62. Yo, dude, respect for being a real programmer. Thank you. I always enjoy seeing real programmers streaming. Real programmers? So a fake programmer? Uh, but yeah, no, thank you. Thank you very much. Thank you very much. And yeah, we're taking a look at the memory allocator, which we're very happy about because we passed some of the tests we had just when you joined. So absolutely great, fortunately. So yeah. Get rid of no AI insert. Oh, I see. That's what you mean. Yeah. Yeah, it is the purpose, right? Understanding the underlying systems, knowing how things work. But yeah. All right, people. All right. So what do we need to do according to our to-do? We need to find the magic numbers and whatever that means, right? So from magic numbers, I mean there was some sort of place that I remember I saw some random number and I was like, dude, this is not ideal. Where was it? Where was it? Do you like practicing lead code or algorithms in general? I usually don't do lead code that much. I do like it though. Depends on the problem. If the problem is like one of those annoying problems, like, oh my God. There's this problem, like, there's this lead code problem, like, I absolutely hate so much that, like, it's really ingrained in my mind. It's like a medium, I think. And it's the one that is like generate all the possible enclosures, all the possible like parentheses, valid, generate all the valid sequences of parentheses that you can have with like n many parentheses or something like that. Uh, it's like, oh my God, that problem is like, I generally wake up in the morning and like, if I ever am faced with that problem, I'm shooting the interviewer on the spot. Like, like I don't mean that seriously, right? It's just that it's an expression, but like, genuinely, like, it is not because it's like really hard because like I personally just think, oh yeah, this is Catalan numbers, right? This is just Catalan numbers. So if you were to ask me about the number of combinations that you can have, it's gonna be just Catalan number n, right? So that's simple, and like it's easy to understand how you could generate them with the Catalan numbers. The thing is like you gotta use recursion and then you gotta do like a bunch of ifs and like it's kind of annoying. So then I'm like, dude, like I know this is a problem in lead code and everything. Like I know how this would work, but it's genuinely annoying to implement. It's like, I just anyways. There are other problems that are otherwise pretty interesting. I'd say there's one about like trapping rainwater. That one is I have not much memory, but I think that one is like pretty cool. I was like, oh yeah, neat solution. Uh, Longest rectangle in a histogram. I think that one's pretty cool too. Um, yeah, but I don't have much experience with the lead codes. Maybe we can have a stream, that it's like solving lead codes for I don't know 4 hours, and then we try to do as many as possible. And then if I don't succeed solving all the problems, we do some sort of punishment. I don't know. But yeah. That's my opinion on lit code. Sometimes, like at work, if I'm like waiting, because once again, I have to use AI at my internship, right? Because that's the way the software industry is right now. What I do is I just open lead code and I just like solve a problem while Claude is doing something. Or sometimes I just play Clash Royale. Like it just really depends, dude. Like if I'm feeling productive, I'm doing lead code. If not, I'm just wasting my time. Um, yeah. Anyways, that was an aside. But yeah, I'm trying to find where the magic numbers that we were mentioning are. I think it's like here. There you go. There you go. This guy. Why 16? Why must the size needed be 16? And partition with if worth it does the same thing. Right? Like 16. Why? It's clear to at least to me, right? It's because that's like, the least amount that you need to do for to get enough to get the minimum size of a block. But I feel it's better if we define here a macro, right? If we define a macro, I think it's gonna be fine if we do it this way. So if we define something like min block size, or like not min block size. Yeah, I guess minimum block size, right? Which would be you need the size of a block to be this able to allocate a free block header plus a block footer. That's like the minimal you need. A block of size 0 would occupy this much space. Size of a block footer. And so the size of a block needs to be able to accommodate for this. But remember that size doesn't take into account the allocated block header, right? So there is a difference that we have in our code base. That difference is the following. That difference is that size of a block is different from space of a block. So in a block, I like to refer to size of the block as like the actual size of the user section, right? Which would be this, right? Right? So that'd be the size of the block. The space of the block, it's like, the total space the block occupies. So it's important to make that different. The minimal block size you can have is the total amount of space you need for these things to occur minus the header, right? So you say like, oh, the minimum size I can have, it's like if I were to have no extra space. So it would be a free block header plus a block footer minus whatever the allocated header is so that I can know what the size should be. So that's why I'm doing it this way. And so now we can just use that between mean block size, right? Min block size. Min block size. Min block size. Hello? Oh, the C extension is just like, anyways. I'll never get tired of trashing on the C extension for VS Code. It's really bad. Anyways. And then here we have another 16. We need to assert that this is at least, min block size. In fact, that's another great thing to include into our isValidBlock function, because now we can check, is the size of the block actually, is block size, so BK size of this block greater or equal to the min block size. We're gonna end up in like trouble with the ghost node and whatnot, because the ghost node is the one that's allowed to skip this. Actually, no, nobody is allowed. So when we access BK size, we also want to make sure that whatever this is, I don't really care. Whatever this is, this thing needs to be, well, actually not size, I think it's set size, yeah. Whatever this is, just make sure that it is assert that the size that you're giving me is greater or equal to the minimum size that a block can have. Perfect. I was happy in the haze of broken out. But yeah, and so we have, let's see. Ooh, Lex X12. Bro, when I sit before my code 4+ hours, I want to die. Life is the hell. Yeah, we've been here for 4 hours and 50 minutes. And this is just the beginning because it's only 12 p.m. and we're going until 5 or 6. So, so yeah, but it definitely gets tiring. Like yesterday, oh my God, yesterday. Dude, yesterday I was so tired of that code. And then I took like a little break of 2 hours and then looked at it again in the night and then found some bugs. But yeah, but yeah, I completely agree with that feeling. Do you use coffee? No, no. Actually, one of the things that I've like been a little bit more serious with is like I don't like to drink coffee. The reason is because like I feel like when you drink coffee to stay awake, that's actually like pretty bad. Like I prefer to have the daunting feeling that I'm about to fall asleep when I shouldn't, because that serves as an indication that there's something I'm doing wrong. Like, if I'm feeling tired through the day, rather than drinking coffee, it's like an indication of, like, ooh, right? There's something I have to change in my life because I'm not resting enough. And so it forces me to fix my sleep schedule. So I prefer to not drink coffee because of that. So now I'm like, okay, no, right. Like, I need to be active and like need to be paying attention to that. If I ever feel tired, the punishment is gonna be feeling tired through the day, not being able to be proactive. So then you fix it because you have to fix it some way, um, rather than tricking the brain into thinking everything is fine. So yeah, so I try to avoid it. I have absolutely nothing against the people that actually drink it because like it's like it actually tastes really good. In Colombia, it's like one of the biggest coffee producers, I think, after Vietnam. Right, Vietnam is like the first. Colombia is across the first 5 places, and so coffee is very common. And I used to drink coffee um, at dinner actually, because like since it's such a common drink in Colombia, like you just drink it at dinner. And so I would drink coffee at dinner. It never really affected me though, or at least I never felt it affected me. Um, I would drink it at dinner and then I would immediately after I touched the pillow. So yeah. Also coca. All right, rather. No. 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 But yeah. So yeah, that's the coffee thing. Um. Okay, what were we doing? Oh yeah, yeah, yeah. The magic numbers. Um. I think we solved that, right? Yeah, I think it's fine. It's fine now. So let me make sure that the program runs with these modifications. Dot slash bins slash test. Yes, perfect. I threw you a follow on GitHub. Yo, wait. Also, thank you for following on Twitch and thank you for following on GitHub. Wait, I completely forgot that GitHub has followers and stuff like that. That's kind of crazy. Thank you so much. Thank you so much. But yeah. So let's see. Do we have the minimum block assertions? Minimum block size. Yes, okay. That's pretty good. When we set the size, we want it to be exactly that, when we have everything. And it should also be part of the isValidBlock function. Yes. Okay, perfect. Yo, awesome. I think those are the only magic numbers that I find, right? Because number 1 is like everywhere. That's totally fine. Number 2, it's everywhere in the names. Okay. Number 3, it's everywhere in the UN32s. Number 4, nothing. 5, nothing. 6. Ooh. Okay. I think this comment is unnecessary. Number 7. Nothing. 8. I swear I have some magic powers, but had one. I generate bugs out of thin out of tested external libraries, brother. No. By the way, welcome to the stream, Best Creeper 21. William Kotoko, thank you for following. No AI developer, real developer. Thank you, Daniel GTMD. Thank you for joining the stream, and yeah, feel free to hang out around. We are coding a memory allocator from scratch. So, perfect. And I think we don't have any more magic numbers. So let's check for every number until 100. Nah, I'm joking. Yeah, of course. Yeah, I think we're fine. So this seems to be perfect. All right. Got rid of the magic numbers. I want to see if maybe we have some here. 1. Case 1. Case 1. This is fine. Yeah. 2. Only doing 32s. That's great. 3. Okay. 4. 4. Oh. 5, 6, 7, 8, 9, 10. Okay. No magic numbers. Great. We got rid of the magic numbers. And now we need to beautify the code. Is the code currently not that pretty? Let's see. I swear, the libc I'm making a backend for is passing to the backend a RAID-only address for me to write it. X Zoe Zox. So Zoe, I imagine, would be your name. Sorry, joined late. With magic numbers, you mean anything hard-coded? Yeah. Like, I just had some hard-coded numbers, and we just created a macro for that, which was called min block size. And yeah. So it's the reason why we're doing it. And we exterminated the termites. We exterminated the magic numbers. Our code is beautiful now. But yeah, no. So now we need to beautify the code a little. Like, this one is more of actually, no. I think we shouldn't do that. I think we should proceed with the tests instead before beautifying the code, because it's possible that the tests show us that parts of the code are like, completely like wrong and stuff like that. And so what we're going to do is we're going to add, let's see, create crazy tests, create these sort of tests and situations that we have over here, over the test file, but like create even crazier ones that are like, allocate that block, partition it, put another one, free it again, free it back. So stuff like that. Let's see. Trust me, you don't want to look at my code. It's held together by magic numbers. Are you living in the US actually? Yes, I'm currently in the US. Because I'm here for college, for studying. I'm currently in college, and yeah, I'm originally from Colombia though. Colombia, South America. And stuff that could be unfun behavior but isn't. I see. All right, yay! Yay. Wait, it's so happy because yesterday we spent so much time trying to think of how to test it, but I think like the assertions are the way. So we just create these crazy situations and then just continue. Anyways. So what can we do? These are like basic tests, right? So let me separate them into categories. So I wanna have over here, and then I think I can close these panels. I don't want to test partition block. That's in the past. Bye. Let's test, malloc tests. Malloc tests. These are the unit tests for each. Then we have the free tests. Well, I feel I would prefer them to be in this sort of, this header. Free tests, and then, ouch. Malloc tests, there you go. Perfect. And then make these be the sort of the unit tests, right? unit tests. And then, of course, these are going to be the realloc tests. Realloc tests. Perfect. Oh, shoot. What did I do? Oh, I pressed F11 accidentally. Okay. And now we're going to do the end-to-end test. Like, well, not end-to-end, but like, you know, crazy situations tests. So I'm going to call them end-to-end. I don't think this is the right name. Let me know, guys, if you have maybe different names. Yeah, and so I think we can just define a function over here at the end that's called bool unit tests that just holds all of them. I was doing it a piece of a drunken hour. Okay, unit tests, and then here we just execute the unit tests. Perfect. And now here, E2E tests. Perfect. And then we create another function. This, of course, returns whatever these guys have done. So return this. There was a beam of praise. Okay. And you. And we put in ands all over. Perfect. And so now the end-to-end tests go here. So you're going to create a bool E2E tests. I'm going to create these. Perfect. So now we have to determine what is it that we want to do. So a good sort of situation. So let's see. There are some things with realloc that I want to test. Well, actually, let's just go in order. So what are some situations we want to test? I feel like bool test. How do we call this test? A great question. What do we do, right? What names can be given to these end-to-ends, right? Like, because it's not like they're exercising a specific path. Like they are going to, right? But we're just gonna do crazy things. We're gonna deallocate and allocate and see that nothing fails. Which is more like a smoke test, right? I guess I'm just gonna call it E2E test 1, right? So, actually, I think it's better if I expand the unit tests and like, if I'm a little bit more conscious about what I include in them. I think for realloc, it's very useful to have the example that we have here with these 3 blocks that we kept thinking about while implementing realloc. Yeah. So I think, okay. I want to preserve these tests, but I also want to do sort of more serious tests where I actually know like what is going on, like with the names and stuff. I guess I'll just keep naming them this way, where I'll just do like bool test, realloc 3, but I want to give them more descriptive names. Okay, how should we name this? Okay, let's just create an end-to-end test. So suppose here I just want, P1, and I'm just gonna nalloc a given amount of memory. Let me actually change the calls to the functions to be just something else, right? Instead of mm3, which I think it's, we've been using all this time, but I think we just called it n3 just to make it a little more, complacent with our naming. would be better. And then nrealloc, memory alloc we replace for nrealloc. Great. Okay. And so now. Okay. If we nalloc, how many bytes? 23 bytes. Let me also create here a function, some sort of function. And in fact, I think we had a function similar to this before, where, you know, we create some random string of a given length. uint32t size. Size. And this guy's size includes null terminator. Right? And so in the intent tests, I'm just going to create a little variable called uint32t current seed. And the current seed is going to be 1. And what we do every time is we simply char star str, it's going to be equal to malloc, the actual malloc. We're going to malloc however many size bytes are needed here. And then actually, I think it's better if we just call this run bytes. Yeah, run bytes. And then, you know, bytes, malloc, size much. This won't have a null terminator. Yeah, and then we just do something like, you know, for every single one of them, I'm just going to use the universal identifier. I'm just going to say bytes at I is going to be equal to the current seed. Then at the end, we increase the current seed. Okay, so we generate a sequence of bytes that is not random, but it's different every single time we call it. And it's just going to be the same letter over and over, just so that we can identify regions of memory easily. And this is something that was suggested by one of our viewers last time. I'm so sorry, I don't remember exactly who it was. I think it was Random Hacker 89. And yeah, so we're going to do this. And then what we can do is whenever nalloc something, we want to mem copy into that whatever it is that random bytes generates. So mem copy into P1, random bytes for size, right? And then the size being, of course, 23, and then 22, right? Something like this. So that way we can populate stuff. So I even think it would be better if we can keep track of things. So remember that we need to also keep track of information not getting corrupted. And for that, we need to know what the original string was, what, you know. So we can create this little struct called block. We're going to do something similar to what we were doing yesterday, but completely detached from it. That's just going to store what data was used for this, the pointer for the actual, you know, memory block that in which it's storing that, and what else? The size, maybe? 32 size, right? So what we can do is we can create a little thing that, you know, called create block, that allows us to create a given block of a size that we pass through. Size. And of course, in C, things are a little different. So now we need to type def the struct to be something entirely. Perfect. Okay, then we create a block, and then what we return is going to be the original data. So I want to have something like this, where I say, you know, block, it's going to be equal to this block. And I say bk.data is going to be equal to malloc however many bytes you need for the size of that, and then copy into it, into bk.data, the information from the random bytes that we're going to have for 23 and then 22. Well, not 23, right? It's going to be size. So size, perfect. And then once we memcopy, we want to do not much else, to be honest. So that's all. That's bk data. And then bk mem pointer, it's going to be equal to malloc that much, malloc size, and then copy into that malloc the data that we have provided. So into the memory pointer, copy of bk data, and however many bytes it was. And yeah, bk that size is going to be equal to size. Finally, we return bk. So that way we automate the process of creating a block. We don't really care about what the block contains. We only care about the fact that it contains unique things that we can identify. And this way, the struct is going to keep track of, okay, this was my original data. This is the memory that malloc provided. Let me compare them as we go. Let me, all that stuff. And so now what we're going to do is we're going to say, okay, right, P1, we do that. We're going to call malloc P1. And so we can create a block called V1 that simply has, well, actually, now that I think about it, yeah, we can just do that. So over here, P1 is actually going to be equal to block. So you want to create a block P1, and that's equal to create block of size 23. Then I say, this should actually be a B. And I say, okay, block B2 is equal to creating a block of size, say 42 or something like that. And block B3 is equal to creating a block of size 12, right? And then what I'm going to do is I want to, keep that information there, but I want to free B2 mem pointer, and then I want to reallocate and realloc whatever B1's mem pointer is. B1's mem pointer to be something else. So actually, this approach with the blocks is really not good at all. I think it just makes it more confusing and it makes everything bad. I think it's better if we simply store the strings that we expect in some sort of array, right? So we're gonna have 3 blocks, for example, char style blocks, right? And it's also gonna be 3. And then what we do is we go for each of them, and then we populate them. So we make data at position I be equal to a random set of bytes, right? Random set of bytes of size, size. Where the size is going to be, I don't know, 40. And then blocks at I is going to be equal to whatever malloc returns when allocating a block of size 40. Finally, we're going to say, well, copy into memblocks whatever data I contains for however long the thing is. Perfect. And so now what we're going to do is we know what the data should be. We have the blocks. We're going to play around with the blocks. So we're going to, free block 1, right? Going to free block 1. So blocks, we're going to free the first block 0. After we free block 0, we're going to reallocate block 1. And then we're going to assert that the data is still there. And we assert with a memory comparison that blocks at, and I guess that of course we reallocate, right? Blocks at 1 is now something different. We assert that blocks at 1 together with data at 1 is still exactly the same, right? I guess here we're gonna need like sizes 3. Blocks at I is equal to 40. So sizes at I is going to be equal to 40 also. When this thing here needs to be a UN32T, and thus it makes it so that we can use sizes right here. Sizes I, and we copy sizes I. And so now we're going to verify that whenever the reallocation happens, the data is still there. Size is 1, right? Too few arguments in function call. What do you mean? Oh, realloc. And then let's realloc to something that is, you know, size is 1, or size is 0 plus size is 1 plus 1, so that it triggers sort of that reallocation that should occur. So we assert that that's the case. The way the heap looks right now is something like this. It's something like, let's see, P1 is, or like, sorry, block 0, block 1, block 2, block 0, block 1, block 2. Great. Then over here, once we free it, it's gonna look something like B0, or this one's like, actually no, it's like all of them are allocated. So I'm gonna cover them in parentheses. And then here, B0 is free, but the other two guys are not. Then when we reallocate, right, B1 is gonna be occupying a lot of space. So B1 is gonna be, you know, B0 is no longer, yet B1 occupies all of this. It's already allocated. Perfect. And finally, B2 is also allocated. So now we need to assert that, you know, the data is still there. After that happens, of course, we're going to return true. After that happens, we're going to try and, you know, we'll try and reallocate blocks 1 again. Blocks 1 is equal to realloc and realloc. And realloc the blocks inside of 1, right? The sizes to size of, you know, 0 plus sizes of 0 plus sizes of 1 plus sizes of 2. So all of the sizes is going to be really huge, really big. And then we're going to assert that no matter what happens, the information is still there. In blocks, memcomp instead of 1. Actually, memcomp, you know, it returns a 0 when they're equal, right? So not memcomp, not this. Data 1, and then we're going to do sizes 1, right? Smooth, thank you very much for following. Yay. So yeah, we assert that the data is still there, even when we reallocate. So how are things looking? Well, we know how they look from before. After, yeah, yo, let's go. But yeah, so the heap after this operation of realloc should look something like this, right? This huge block is block 0, and it's no longer free. right? I think the way we can materialize it is how? Hmm. So this thing is free, right? This B0 is free all the way. B2 is still allocated, and then B1 ends up reserving a space for themselves in a little island in the Bahamas. Right? B1. It's gonna be huge. Okay? And so actually then here. 1, 2, 3, 4, 5, 6, 7. There you go. So it's occupying all of that, and same here. 1, 2, 3 here, 1, 2. Right? 1, 2, 3. Perfect. And so now we can that's exactly what we should see. So that means that when I, you know, run blocks what? So maybe now I want to reallocate 2. Want to reallocate 2 to where? So blocks 2, I want to move it to something that is the same as sizes like, I'm not sure what it should be. Reallocate to something that's a space like of maybe 56. Not sure. Actually, I do know. Something that's of sizes B1 or like B0. So 0 plus sizes B1 plus sizes B2. And so that way we're going to trigger the thing where it has to merge with this guy and then, not do much after that. Yeah. And so now we need to assert that the memory contained by blocks 2 is still preserved. Stata 2, just sizes. Oh. Something important here. Yeah, no, I guess so, right? Sizes 2. Mem comp. Right. So one thing we could do after we perform all of these reallocations is we can say copy new data, right? Mem copy into blocks 1. We want to do what do we want to do? Maybe we want to, we copy the memory here. Yeah, I feel that this is enough, right? It's a little comprehensive test of what should be happening. And finally, this would be the last, the state of the heap. At last, it should be, yeah. And then here, right? Here we're gonna have another block. That's what it should look like. So then we return true. Let's see. Can we run this? So end-to-end tests. Then we're gonna return E2 E test 1. Okay. Now if we make test and then we run it, we didn't fail any assertion, which is awesome. Oh shoot! We're failing something. Reallocated block 192 to address 1,800,000,000. Oh no. Come on, dude. Come on. Come on, please. Anyways. What's going on? Also, why didn't any... So what scares me is why didn't any of the asserts trigger here in the main file, right? Because we see that it says a huge number. So when we debug realloc, and then it's something like reallocated, yeah, however many. So here. What is going on with this? Oh, dude, oh my god. This is not the way you calculate that. These guys should be on the right. Okay, from the new pointer, we subtract the mem float to know where that thing is. And then we subtract allocation block header. Okay, I was getting scared. So it was just an error in the log rather than an actual error. Yeah, okay, now it's more normal, right? It allocated to block 336. Perfect. Awesome. So it seems like nothing is failing so far. Yeah. And so now we want to... What do I want to do? I do think we want to... See, for some reason, the idea of the block struct, it's still, dancing in my mind. And the reason for that is I wish it was a little bit more automatic, the process of tracking, what data should be there, what should be happening. Because, okay, let me think about this a little more deeply, and let's think about it so that we can know, what to write. So we're going to store the data. We're going to store the memory pointer to where we are. And we're also going to store maybe, not the size of the block, but instead the data size, right? Perfect. And so what we're going to do is we're going to grab this block struct here. Of course, put the name over here. Yeah. And then after this happens, we're going to create some helper functions, right? So we're going to create a block function that's called create block. And what create block is going to do is it's going to allow us to say, give me a size and I'll give you a block that has that much. So size, right? And then here we say just ran by, like, the block. So maybe we create a block bk. Then we say bk.memPointer. bk.memPointer is equal to what? Oh, Softworm7. Thank you for following, and same for Ponchu FPS. So yeah, block memPointer. We're going to call malloc on this, the actual malloc, to allocate size many bytes. Then we copy into it whatever random bytes decides to give us for that many bytes, and we're going to be that much data. Then we know that, and this actually shouldn't be the mem pointer, this should be the data, because the mem pointer comes now. The mem pointer will be equal to our implementation of malloc. And to that implementation of malloc, we need to write the data that we have. So bk.memPointer, and then we write in whatever bk data has already, and then size. Finally, we make the size of our data equal to size. Perfect. And I think this hasn't caught on. Yeah. Okay, and finally, at the end, we return the block. Right? So that's a good thing, right? After this happens, we want to be able to say something like, block, and then here, realloc block. So what it's going to do is it's going to sort of emulate what realloc would do. So it does 132T size, and then you need to pass me which block we're talking about. Block. And this guy is a reference, actually. And so now what we can do is... Actually, no, it's better if we do it this way. What we can do is we're going to just do exactly what we did here. So whenever we realloc, what we need to do is recall nrealloc and make our, let me call this bk. And make a block's memory pointer be equal to whatever new thing they give us for the size that we want. Then we change the bk size, data size, to be equal to size. And now we're going to modify our data to be a little longer than what it should be, right? So yeah, right. And so we'll then copy into this. I think it's also better if we simply, actually, yeah, now that I think about it, give me 1 kilobyte of random bytes all the time, so that now I can just copy to the memory pointer whatever the data pointer is pointing to, but I'm gonna do so only size many. So that way the data is always like a constant letter, like say A, and then I just simply control the size of how much I want of that to live inside my block. Finally, we return, the block that has been given to us. Perfect. So we have the mem pointer, the data size, bk mem pointer. Actually, I think yeah, sure. Great. Then what else do we do now? I'm like, what do we do? We need to, is there anything else we need to do? No, we update the main pointer, we update the data size. We don't need to update this because this already has all the data it needs. Sorry, this guy we don't need to update because it already has like 1024 bytes. So now we copy the memory, we're fine. Yeah, this should be fine. And this should also carry the weight of the assertion. So every single time we alloc, we want to make sure that this thing is holding the right data. So let me make sure that bk.memPointer, right? It's not memcopy, it's memcomp. Okay, mem comparison. Compare these two up to data size many bytes. And they should store and they should have the same. Jewel Eater, thank you for following. Jupiter, but with an O. Thank you for following. Yeah, welcome to the stream. Welcome to the stream. So currently we're just creating these functions that will allow us to test that like things are going well and that data is not getting corrupted or anything like that. So now we just do a mem comparison on a bk.memory pointer. Yeah, now they still have to be equal. bk.data and then bk.data size, right? And perfect. I actually think, a little bit of an unpopular opinion, but I want to make, yeah, I'm not sure if I want this. I think size is fine, and then size is fine. I don't want remnants of stuff. So data should be able to, we should be able to mem copy. Actually, why am I copying here? Yeah, this shouldn't be happening. Perfect. Yeah, that's the right way to do it. Because then over here we say, well, bk.data is going to be equal to more random bytes of the size that you gave me. And then I change the size of the data to be that. And then finally I copy into the non-pointer all of the data that I have for that much. And then we assert that the data is exactly the same. Perfect. Great, so that's for realloc block. whenever we free a block, we don't really care about that block, and so it's gone forever. Um, yeah. So I think I'm just gonna create here like you know, a function called free block just for the sake of completeness. And you just want to tell me which block you want to free. And all we do is just say bk.mem pointer, you know, and free on that. Then nothing else. Perfect. So now, well, this returns void. Okay, so now we can test our things. And let me actually translate this end-to-end test one to this new interface because I think it's a lot easier. Since the comparisons are performed sort of automatically. I think I can just do new lines here. And then on this side have this, and on this side have that. Perfect. Well, actually, no, because as I edit the file, it's gonna create new lines, and so it's you know. So let me copy this and then paste that. Hello, Joyita. So, hi, do you make a living from this, or are you a student? I am a student. I'm a student in college. So yeah, we're doing this for the sake of learning. Right? Yeah. Uh, so yeah, we've been working on it for a while, for a big while, and I think we are nearing the end of everything. We still have to measure the performance and all of that stuff, but at least we're gonna have a working memory allocator, and then we worry about performance and etc. So yeah, I mean, I feel it's like relatively performant, right? But maybe there are things that we can optimize. Yeah. Anyways, so here instead of creating all of this stuff, we can simply say, blocks. Then I just want to store 3 blocks. And then I say, well, for each of those 3 blocks, int I is equal to 0. If I could make a living out of it, that would be wonderful. But of course, right, it's difficult to make a living out of learning. That's very interesting. I used to be a BI analyst and worked extensively with data analytics. Yo, wait, what brought you here then? It's like a little bit of a strange profile to be calling to like a memory allocator stream. So what brought you here? Or are you, did you maybe change and didn't do any more BI analysis and instead focused on something else? Like, yeah, tell us more about you. In the meantime, I'm gonna be here writing this. Let's set I is gonna be equal to create depth of size, I don't know, 40 probably. Yeah. So now we create the blocks. We're gonna free this blocks at 0, and then I'm gonna say, well, blocks at 1 is gonna be equal to realloc block, blocks at 1 to what? To maybe, something that has the size of our previous block 0. The data size plus my size. Okay, so guys, what do you think? Like, should we make a test random? Should we create random tests where they just generate random values of the size of the blocks and then just free and allocate random stuff? Should we do that? Almost like a fuzzer. Like, it's kind of like a fuzzer. What's the name of your keyboard? My keyboard is like a keyboard that I got for free because somebody was gonna throw it out. And I was like, oh, I don't have a keyboard, please give it to me. It's this keyboard. It's called the Corsair Gaming K68. There you go. Yeah. Oh no. Yep. So here when we're talking about like, should we approach this with a more like, you know, fuzzer sort of approach where we just do random stuff, and then out of so much randomness, there has to be some bug that gets caught in the net. Um, right? Because how do we do it? Because then that would imply like, you know, creating a thing that randomly picks between freeze and reallocs, and in that respect, you know, no use after free, no nothing like that. So let me think about it. I think that should be fine, right? Like if we just create a machine of random stuff, that would be more than great. Yeah, yeah, I think we can just do that. Sort of a fuzzer type of approach. Um, we're still gonna have this one, but instead of doing it manually, we can just have a random, right? So the way we're gonna do things here is, how do I generate a random number in C? That's a great question. I don't know, but yeah, maybe we can generate like random numbers for the sizes, and then to pick what action to take, we simply, you know, we simply what? Hmm. Let's see. I think it's already 1 p.m. Right? So I think we can take a break here, maybe, while we think of like what we're going to do with the random tests and stuff. Um, and then after that, we can come back and continue coding. I say that mainly because I have to eat lunch. I haven't eaten lunch, and yeah, and then maybe we get a little bit of a fresh mind, and then continue with this, knowing sort of more how we want to do the further approach for these tests. Yeah, yeah, I think so. Okay, so everyone, we'll see you back in like. I think so. So what I'm planning on doing is I'll simply do the starting soon screen, and we'll just put 30 minutes on it. I think somebody got angry at me because, you know, I put like a rest of 1 hour. But honestly, you know, so do you guys prefer one or the other? Because the reason why I do it like that is because I just want the VOD to be one huge thing on what we did in the day. I know some people don't like it though. And so yeah, I guess we can just end the stream and then I'll turn it on back in 1 hour when we're back so that you can get the notification that we're gonna continue. So yeah, let's do that. All right, everyone. Um, as I mentioned, let's take a break for now. Let's take a small break. Why just not pause it? Like pause it? Yeah, we could pause it with something like this, right? But um, like I'm not sure. Like, which one do you guys prefer? Because some people are like, oh no, I don't want to wait. Because it's gonna be 1 hour, right? So it's gonna be like starting soon and then 60 minutes. So I'm not sure. Like, I guess yeah. No, let's do it. Let's just pause it and if people, just put a timer of 60 minutes and or if you have it in the background, you're gonna hear my voice uh when when everything happens. Okay, that's fine. Okay, okay. Let's do 60 minutes. Okay. All right, people. Bye bye. Wait, actually, I realized that I think it's better if I end the stream because OBS starts consuming a bunch of memory. Since I mean, right, I'm probably gonna watch a YouTube video in the meantime, like and eat and stand up and stuff, and and then the computer's really slow. So let's do this. I'll end the stream and then I'll turn it on again when we have to come back, so you guys get the notification, and then we continue. Okay. All right. I'll see you guys, and yeah, bye bye.